have a problem, or it will have a distraction for the speakers during their presentations. After the presentations are done, particularly for the invited speakers, we'll have a question and answer session. During that time, you can unmute yourself, you can come in front and you can ask questions. Rest of the time, I would ask all the audience, apart from the speaker, to please keep yourself in a muted situation. Don't come, unmute and start disturbing or problems for the speakers. And for today's webinar, we have different kind of presentations and talks. For the invited speakers, they will have a presentations of 20 minutes, and for the paper presenters, we have the presentations for 10 minutes. So without going into the detail, I would like to thank all of you for joining. So first of all, we'll start with an introductory address by the convener of this seminar, or webinar rather, and also the head and Department of Physics, Narajole Raj College, Dr. Tapanendu Kamila. I would like to welcome him and to give his introductory address. So ladies and gentlemen, please welcome the convener of this seminar and the head of the Department of Physics, Dr. Tapanendu Kamila. I am handing over the microphone to him. Sir, you can please start.
Okay, Dr. Pradhan. Good morning, everybody. Thank you all for joining us here in this two-day international webinar, Recent Trends in Nanomaterials and Nanobiomaterials, organized by Department of Physics, Narajole Raj College. We are feeling very blessed to host this international webinar, particularly in this time during this lockdown situation due to pandemic of COVID-19 virus. Just before get started, I would like to express my gratitude to our Honorable Principal, Dr. Anupam Parua, who is also the innovator of this session, and respected invited speakers from various parts of India and abroad. Dr. Subodip Ghosh, Associate Professor, School of Chemical Sciences, NISAT. Dr. Ravikiran Saripulli, Postdoctoral Fellow, Department of Quantum Information and Nonlinear Optics, Tulane University, United States of America. Dr. Udayan Maiti, Assistant Professor, Department of Physics, IIT Guwahati. Dr. Kallol Roy, Postdoctoral Fellow, Center for Advanced 2D Materials, National University of Singapore. And honorable teacher participants from other institutions, my dear colleagues, my beloved students from our college and other institutions, to all of you who so generously responded to make this event so graceful. Truly speaking, we could not have done it without you. Now, as we all know that the current world is incomplete without the revolutionary word, the nano. It is well known that nanomaterials are special for several reasons, but for one in particular, their size. The material particles having dimension in order of 1 to 100 nanometer are called nanoparticles. This is known to us. Many novel electrical and optical, electronic, etc. properties are observed in nanoparticles owing to their high surface activity. In spite of their very small size, they have a big impact on our everyday life that makes them exciting and important to know about. The nanoparticles have created the considerable attention from the field of nanotechnology to targeted drug delivery. Now, as for example, the colloidal gold and silver nanoparticles have accomplished extensive importance in therapeutics and diagnostics of treatment of malignant tumors, sensing of different biological molecules and chemical elements. Also, silver nanoparticles have very good antimicrobial property, having application in preparation of antimicrobial lotion, ointment, soap, food packaging materials, etc. Now, similarly, zinc oxide nanoparticles having application in preparation of sunscreen lotion, different moisturizers, etc. Correspondingly, nanotechnology has immense application in food science and food industry, from food packaging, sensing of pathogens, along with different chemical molecules, testing of food quality, the producing of new products and ingredients which increase the efficiency, bioavailability, functionality, flavor, as well as nutritional value of food products. Also, for targeted delivery of nutrients, etc. As for example, we can say that the oil droplets are dispersed in water and have been used in many food processing factories for preparation of fruit juices, soft drinks, dairy drinks, etc. beverages. We all know that the name of vesicle and solid lipid nanoparticles. The vesicle and solid lipid nanoparticles, as well as other biomaterials, have immense application in targeted drug delivery. As a result, we have become more and more interested in their technological and biological aspects and have organized this international webinar, Recent Trends in Nanomaterials and Nanobiomaterials. I hope that the webinar will enkindle the academic activity and imagination among the students and other participants. Thank you.
Thank you, Dr. Camilla, for his wonderful introductory address. I'll go to the second part, and we'd like to formally inaugurate today's webinar. And in order to do that, I would like to welcome the inaugurator of today's program, who is also the honorable principal of our college, as well as the president of this two-day-long webinar, Dr. Anupam Parua. So please, ladies and gentlemen, please welcome the principal of our college, Dr. Anupam Parua.
So first of all, I wish you a very good morning to all of you, the participants, the researchers, the speakers, the organizers, to each and everybody. Before going into the detail of the topic, or before going into the seminar itself, I would like to point out certain facts which are associated with the college that is to be taken as a very, very short glimpse of our college. First of all, in Narajole Raj College, we believe in management and not in administration. So what does it mean? It means that we do not believe in simply following the rules and norms. We are to go beyond that. We believe in going beyond that. We believe in the process of getting the things done through and with the people in formally associated groups. So we in Narajole Raj College believe in man management, and we are hoping that only this style of management can produce results like the one we are witnessing here, a two-day international seminar, or you can call it a webinar as it is held in web, the recent trends in nanomaterials and nanobiomaterials. In short, these catchwords are very recent trends, so I am to reiterate that, RTNN. So first of all, I thank the organizer, the Department of Physics of Narajole Raj College, for arranging such a beautiful program. And I hope that the program will be a success to all the stakeholders associated with this kind of event. So before going into the detail, again, I come back to the glimpse of the college. First of all, the average age of the teachers and staff members of the college is very, very low. Very, very low. And in our college, if you can go through our website material, then you can find that we have a very small number of associate professors. What does it mean? Most of us are assistant professors. That means we are young, we are energetic. So from the point of view of the average age of the teachers and staff members, two benefits are emanating. At least it is in my mind. First of all, the level of energy, the level of dedication, the level of commitment, the fearless attitudes towards approaching any job, the inculcation of finding newer jobs, all are very, very high. And another thing is that, what? And another thing is that the reception of technology, the newer technologies are very, very high here. So while holding such a seminar, we are in an advantageous position in terms of young, energetic persons around me to help me out in organizing such a program. And another thing is that the set of people we are having are technologically very, very interested. They have great interest in technology, and as such, and only for that, we have the courage and we have the confidence to arrange such a program. Sitting in a rural belt 40 kilometers away from a town called Midnapur, we are sitting Narajole, which is 40 kilometers away, which is a totally rural belt under a Gram Panchayat. So sitting there we have the courage to arrange or organize such a program, an international program, and involving truly international persons, though of Indian origin, but they are truly international persons. So another thing is that when the coronavirus came in, so we felt that the situation would be challenging. So how to face the challenge? So being academicians and not being medical practitioners or medical professionals, we cannot participate in the process of removing or fighting the coronavirus directly. But then we have to contribute to the society. So we felt that we are to contribute. And the contribution must come from two different fronts. One is the academic front and one is the technology front. And from the academic front, we sensed it proactively. So we believe in management, so we believe in proactive thinking. So we reacted, we didn't react, we did proact. So under proactive thinking, we put a notice on the very first day of the closure of the college due to coronavirus effect. So in that notice, I mentioned that we are to develop web materials for the students, we are to arrange web classes for the students, and as the energy level of our staff members are very, very high, we didn't have any problem in arranging such classes or putting up such materials in our college website. So that is the academic front. Now comes to the technology front. As the technology, we in our college is maintaining one specific committee, and it is a peculiarity of our college. We are maintaining a specific committee in the name of Technology Committee. And the Technology Committee consists of very young, energetic, dedicated, committed members who are also having great interest, though they are not from basic science or computer science, but they have such an interest in technology that they are able to manage, to me, almost everything which is required to handle the situations we are facing. So we are having a technology committee consisting of Professor Borun Raut, Dr. Mohammad Aziz, Dr. Abhijit Pradhan, Dr. Shreyoshi Jana, Dr. Poulomi Odhikari Mukherjee, Sri Ashok Bhatto, and Professor Tanmay Goswami. All of them are very much contributing to the cause whenever I felt it necessary, and whenever I asked them to do anything, they are always ready to provide me the support which is required by any institutional head to organize such a program of that magnitude. Then come to another important aspect of the college, that is the quality initiative or quality management. And we are fortunate to have a very vibrant IQAC, Internal Quality Assurance Cell, under the stewardship role of Dr. Nilanjana Bhattacharya, who always take great initiative in conceptualizing and initiating newer ideas, and then through different sources or through different support systems, she enables to materialize the initiatives which are thought of. So the rate of materialization and actualization of quality initiative is also very, very high in our college. And to me, I must admit that to me, she is a real source of inspiration for taking new initiatives that will guide the college into a upper tier. I personally thank the Department of Physics, headed by Dr. Tapanendu Kamila, for having the courage, first of all the courage, then the actualization of the program. We should have the courage to organize such a great program, such an international program involving so many persons from outside Bengal, at least outside Bengal, and those who are having their job outside India. So I personally thank Dr. Toponendu Kamila for his initiative, and I also thank the departmental committee members, Dr. Abhradip Pradhan, Dr. Arif Iqbal Mullik, Professor Surajit Dhara, Professor Sumanto Hait, and last but not the least, Supal Kumar Barik. So suppose Dr. Pradhan, he is having a twin role. He is a member of the technology committee, so he is handling the technology affairs, and then he is also handling the departmental affairs on behalf of the Department of Physics of Narajole Raj College. Now I am going to congratulate the speakers for their effort in coming and joining in the seminar, two-day national seminar. First of all, I am grateful to Dr. Subhadip Ghosh, National Institute of Science and Education Research, NISAR, Odisha, India, Dr. Ravi Kiran Saripalli, Tulo University, United States of America, Dr. Uday Narayan Maiti, Indian Institute of Technology, Guwahati, India, Dr. Kallol Roy, National University of Singapore, NUS, Singapore, Dr. Sudipto Pal, University of Salento, Italy, Dr. Haradon Kole, Geobak, National University, Republic of Korea. So I personally and on behalf of all the authorities of the college, thank you for coming and joining in the national seminar, in the international seminar organized by the Department of Physics, Narajole Raj College today and tomorrow. I once again feel grateful that you are coming into the seminar in different roles, and I hope that the participants of the seminar will be greatly enriched by your presence and by your deliberations. I thank you all, sirs. Without paper presentation, no seminar can be complete. So we arranged for presentation of papers by different presenters from different institutes, not within Bengal only, but also from outside Bengal. So I first of all would like to thank Piyush Kanti Samanto from Kontai PK College. He will be a presenter of his paper. Dr. M. Krishnabeni, he is from Tamil Nadu. Dr. Vidyut Haldar, he is from Damdam Motijil College, West Bengal. Those three papers will be presented today, and tomorrow there will be 10 papers to be presented. One by Mr. Bappa Sonakor, he is from Panchkura Bonamali College, West Bengal. Dr. Kalipodo Bakura, he is from Tamranutta Mahavidyalaya, West Bengal. Dr. Sweety Join, he is from Madhya Pradesh, Samrat Ashok Technological Institute, Madhya Pradesh. Dr. Amit Kumar Bhuiya, Government General Degree College, Gopiballabhpur 2, West Bengal. Dr. Devashish Otto, Government General Degree College, Kharagpur 2, West Bengal. Dr. Somosundar Moti, Government General Degree College, Kharagpur 2, West Bengal. Dr. Kaushik Chandra, Midnapur College, Midnapur, West Bengal. Dr. Gajendranath Maiti, Ashutosh College, Kolkata, West Bengal. Dr. Ushoshi Dotto, he is from Jhargram Raj College, Jhargram, West Bengal. Dr. Tapos Ghosh, he is also from Jhargram Raj College, West Bengal. So there will be 13 papers to be presented, 3 today and 10 tomorrow. So it's a huge effort on the part of the Department of Physics, and I personally and on behalf of all the authorities of the college, thank you, the departmental committee members of Department of Physics, and especially Dr. Toponendu Kamila, whose role in organizing the seminar has been praiseworthy. And now we have another program to have. Within the very short span of time, but with great heart and excellent level of efficiency and dedication, we are able to come out with a book consisting of abstracts of the papers to be presented and the lectures to be delivered by the speakers in their different capacities. So I would like to ask Dr. Obrodhi Pradhan to unveil the e-book that we are publishing today, and we hope that during the course of time, we will be able to have the publication in material form in hard copy. So today we are publishing the material only in soft copy, but in future, when the situation becomes normal, we will be able, or we will be definitely able to come out with the physical copy of that. So I would request Dr. Pradhan to unveil the e-book that we have prepared for this seminar.
Thank you, sir. I'm going to show the book of abstract in front of you.
Is it okay?
I hope you will be able to see the book of abstract pages.
It is coming. It has not come yet.
Sir, can you see
it? Is everybody seeing that?
No.
Dr. Camilla, are you seeing that?
No, sir.
Yeah.
Presentation mode stop.
Okay, I'll try once more. Just bear with me.
Okay. No problem. This is a new world to all of us, so technical glitches are bound to come in. So we have to handle it with confidence. No problem whatsoever. So I am going into the next part of my delivery. Actually, I have come a long way, so I do not want to take more time. I am not a man of physics. I am basically a man from commerce, a student of commerce. So
is it visible now?
Not yet. Yeah.
Okay, sir.
Visible. Okay. So it's a great effort on the part of Department of Physics. So we can see the e-book in respect of the international webinar, today international webinar, titled Recent Trends in Nanomaterials and Nanobiomaterials, in short RTNN. So thank you, Department of Physics, everybody in the Department of Physics. And as I have mentioned, I am a student of commerce, so physics is not my cup of tea. So I am not going to destroy your time, any more time. So I would like to complete, and before signing off, I formally announce the inauguration of the two-day international webinar on recent trends in nanomaterials and nanobiomaterials. And I hope the deliberations of all the invited speakers and the deliberations by the paper presenters will be really benefiting for each and everybody who are or will be participating in this two-day national seminar. I hope all the best for the organizers of the seminar, for those who are in the support system, working in the background, to have the seminar a grand success. And before signing off, I thank each and everybody associated in different roles in this international seminar. Thank you all.
Thank you so much, sir, for your warm welcome speech as well as the inaugural speech. Indeed, without the help of sir's motivation, we could not actually been succeed to make this webinar a successful ceremony. Sir has always been a source of motivation and enthusiasm for all of us. So thank you, sir, once again for your warm inaugural talk.
Now, Dr. Obrodhi Pradhan, Assistant Professor, Department of Physics of Narajole Raj College, will deliver the welcome address. I am handing the microphone to Dr. Pradhan. Dr. Pradhan, please.
Thank you, sir. So now I'll formally would like to welcome all of you. I'll start my presentation. Just once again. So as I already mentioned that we are having a 2-day-long international webinar on recent trends in nanomaterials and nanobiomaterials, which is in short called RTNN, which is held in June 14th and 15th organized by the Department of Physics, Narajole College. So in this ceremony, I would like to welcome, first of all, the Honorable Principal and the President of this webinar, Dr. Anupam Parua. I would like to welcome the IQAC coordinator as well as the member of that. I would like to welcome all the members of the Department of Physics who have been consistently helping us in order to make this webinar a grand success. I'd also like to welcome the college faculties, students, and non-teaching staff to be here. I welcome the external faculties and students from all other colleges. I also welcome the technical subcommittee members who are consistently helping us to keep this webinar in a smooth conduction. Friends, I'm not going to go into the detail of the significance of the word nano, but we all know that why this is so important for today's life. Indeed, nano, in spite of its very small structure, has a great impact in today's life. Because of its small size and unique band structure and electron confinement, nano has become an immense source of interest in the world of science, particularly in physics, chemistry, as well as material science. Nano has become important for not only into the detail of the novel physics, but also has become an immense source of technological aspects. And that gives us the motivation to have this kind of webinar in front of all of you, particularly for the students who are becoming more and more interested in the field of nano. UGC has also recently introduced a syllabus containing the nanomaterials in the 3-year undergraduate program. So in order to have this webinar, an enriched one, we have invited 6 eminent and dignified speakers across the world, which already our principal, Dr. Parua, has already told you, but I would like to show their name one by one. So for the keynote address, we have Dr. Shubhadeep Ghosh from Nizar, Odisha. We have also 5 more invited speakers across the world. Dr. Ravikiran Saripalli from USA, Dr. Uday Narayan Maiti from IIT Guwahati, Dr. Kallol Roy from NUS Singapore, Dr. Sudhip Topal from University of Salento, Italy, Dr. Haradhan Kole from Jeonbuk National University, Republic of Korea. Apart from such eminent invited speakers, we also have 13 paper presenters. That gives us the happiness that how much the people have been interested in order to participate in this webinar. We have 13 paper presenters across India in order to make this successful. I welcome all of them. And with that, I conclude my welcome speech. Thanks for attention.
Thank you, Dr. Pradhan, for your nice welcome address.
Now it's time to start the formal procedures of the seminar. So first of all, we'll start with a keynote speaker talk. So I'd like to introduce him in front of all of you. So the keynote speech will be just one second. Sorry. Yeah. Yeah. The keynote address will be delivered by Dr. Shubhadeep Ghosh, who is Associate Professor in the School of Chemical Science in Nizar, Odisha. Dr. Shubhadeep Ghosh has done his MSc from Vidyasagar University, followed by a 4-year program of PhD from Indian Association for the Cultivation of Science, Kolkata, followed which he has done a postdoctoral fellow, was a postdoctoral fellow in the University of Texas in Austin, USA for 2 years, followed by a postdoctoral fellowship for 1 year in Riken, Japan. The specialization of Dr. Ghosh is in molecular and single molecular spectroscopy. He has published 50 plus very wonderful research journals. He has also got awards from many places, from Ramanujan Fellowship, DST, CRB. He has also qualified for the CSR NET GRF and also West Bengal College Service Commission. He has also been awarded with a gold medal in Vidyasagar University in 2002. And today, he is going to talk about insight to the photophysical processes in semiconductor, quantum dots, and carbon dots. So, ladies and gentlemen, please welcome the keynote speaker, Dr. Shubhadeep Ghosh. Dr. Ghosh, you can start your presentation and you can unmute yourself. Sir, I think your microphone has been muted. Please unmute yourself.
আবার রিলিং দিয়ে ঢোক।
It seems like there has been some technical difficulties. I would like to request all the audience to please bear with us for a few moments.
Now it's okay. So am I audible now?
Yeah.
Yes, okay. Just check it. Am I audible now?
Yes, sir. You can start, sir.
Okay, thank you. Just give me a minute. So I'm completely new to this system. Present now. So I hope everybody can see my slide now. So first of all, I'd like to thank Dr. Tapanendu Kaminda. Am I audible now? Sorry, I'm repeatedly raising this question because I'm
yes,
not.
Yes, sir, you are audible. You can make the presentation mode in full screen.
Okay, can you? Okay, full screen. Great. Okay, now it is full screen. So, first of all, thank you, and it's a great pleasure for me to deliver my talk online. And this is the first time in my life I'm presenting my research topic in online, and hope everybody is safe and inside home. And I also wish this COVID scenario will get over very soon, and we can again hold the conference in your college. And I'm very much excited to visit Narajole College. I never been into that college. First of all, I'd like to thank Professor Anupam Parua and his wonderful talk. I have learned many things from his talk. And also my long-term friend, Tapanendu Kaminda. I know him from my school time. And also Dr. Abhrodip Pradhan for his speech. And I would like to thank many others who are sitting in the audience. Enjoy this online session. This is really wonderful and principal for organizing this type of webinar. Okay, so today I'm going to present. This is the topic of my talk: insight to the photophysical processes in semiconductor, quantum dot, and carbon dot. So everybody knows that I'm from NISA, so I'm not going to this part. I want to skip this one. And now I'll start my research topic. So this is regarding the FRET study. This is fluorescence resonance energy transfer from a quantum dot CDT ZNS, that is energy donor, to an acceptor molecule, rhodamine 60. So this is the acceptor. I think everybody can see the cursor here. So this is the acceptor molecule and this is the donor molecule. So now what happens if I excite the molecule with some laser light? Upon addition of this acceptor molecule, I found the emission of donor is quenched. So this could be due to various reasons. So first reason, it could be energy transfer, or second reason, it could be electron or hole transfer. So now if you look into the band gap alignment between this couple, this is quantum dot, this one, and this is the rhodamine 6G, the organic dye, you will find neither electron transfer and, sorry, not the...
Your voice is not audible at all, sir. Very, very low audio we are getting.
Oh, okay. Am I audible now? Is it okay?
Yes,
Right? This is the
yes,
problem.
sir, it's okay from me.
Okay, but I don't have any other option. You have because initially I tried with this microphone, but this microphone is not working. So that's the problem. Okay, I'm speaking loudly. Hope you can understand, or you can listen to my voice. Is it okay now at this moment? Can you hear me?
Absolutely, okay, sir. Please continue.
Okay. So this is neither electron transfer nor hole transfer is possible. This is thermodynamically forbidden. So now on the process behind the quenching of emission of quantum dot, it could be the energy transfer. So energy transfer is a non-radiative process and it happens due to dipole-dipole coupling. And the prerequisite for energy transfer is there must have been a good spectral overlapping between donor emission with the acceptor's absorption spectra. So here this solid line, it shows solid black line. Okay, this is the absorption spectra of quantum dot, and this one is the emission spectrum of quantum dot. Now, and also the red one, this solid line is the absorption spectra of rhodamine 6G, and this dotted red line is the emission spectra of the acceptor molecule. That is rhodamine 6G. Now, if we look into the overlap between the emission of donor, means who is donating the energy, with the absorption spectrum of the acceptor who is accepting the energy, there must have been some good amount of overlapping, and you can see there is some shaded portion. This shaded portion is basically indicating that overlap zone. So now the overlap, there is a significant amount of overlap. That means energy transfer is possible, and the quenching is due to the energy transfer only. So this is a CDT ZNS quantum dot. I represented this quantum dot here, and this is the acceptor molecule, nothing but this is organic dye molecule. And these two molecules are oppositely charged because this quantum dot has a oleic acid capping agent, at the outer surface that is negatively charged and rhodamine 6 is positively charged. So obviously they will form complex when I mixed it in water. Okay, so this overlap portion that is shown by this shaded portion, it is denoted by overlap integral. So more the value of overlap integral, more will be the energy transfer efficient. So here the value is 4.5 into 10 to the power 15, that is is indicating significant amount of overlapping. So now I synthesize this quantum dot, followed by the sum of this quantum dot through TEM, and I found that the size of quantum dot is around 4.5 nanometer. Okay, and this is showing rotational anisotropy decay. What is rotational anisotropy decay? So this is representing how fast this is my molecule, how fast it is rotating. Now here this curve is signifying that rotation is very fast and it's finished within 230 picosecond. And here rotation is very slow. So this is showing the rotation of the complex, that is rhodamine 6 along with quantum dot. And here it is showing the rotation of only rhodamine 6G. Now when there is only rhodamine 6G, there is no quantum dot, I can find the rotation is very fast, because obviously this rhodamine 6G molecule is very small. Hello, am I audible now?
Sir, your presentation mode has gone off. You have to turn it off once.
I know. It was disconnected for some.
Actually, sir, because of some unintentional interruptions, if someone opens the presentation mode, your mode will go off. That's the problem.
Okay, Abhijit, is it visible now?
Yeah, sir.
It's
coming, sir. It's coming. You have to open the presentation.
I have to open the presentation. Okay, now it is visible completely.
Yeah. You can go in full screen mode. Yeah.
Sorry for the interruption. It's happening again and again. Okay, so it shows that the rotational anisotropy becomes slower when this rhodamine 6G get attached. It's attached with the quantum dot. Because the size, when rhodamine 6G is attached to the quantum dot, the size is much bulkier, and obviously you are no longer presenting. Same problem.
The problem is some people actually, when they are entering, they have started presenting. Mr. Gopalpal, please, I request you to stop your presentation mode. Please, kindly don't interrupt the speakers in between. I've already told, I'm repeating once again to the audience, please don't start your presentation mode and don't disturb the speakers. It's a request. Sir, you can start it. Sorry for the interruption.
Okay, no problem. So everything is fine now?
Yeah, but you have to start the presentation mode.
Okay, and can you see my screen?
No, sir, not yet.
Is my screen?
No, sir. You have to start the presentation mode. You have to start. The mode is not on.
I have to start again.
That's the problem, sir. Every time someone comes in, your mode will go off. You have to manually start it again.
Okay, now it is fine.
It's coming, sir. Yes. Yeah, now you can open the presentation, sir.
It's already open. Can you see it?
Yeah, it's coming, sir. Please continue.
Okay. So when this rhodamine 6 is from complex with quantum dot, now the size is bulkier, so you can see the rotational anisotropy time gets longer. So this observation indicating that there is a complex formation between these two molecules, and this complex formation will lead to the threat. So this is showing the quenching of donor emission of the addition of proton. We find the emission of the donor is decreasing at the cost of increasing the emission of the molecule that is the signature of thread. Now, when I normalize the area under curve, it shows there have been an isoemissive point between the emission peak of donor and acceptor. This isoemissive point indicating that donor emission is coupled with acceptor emission and they are in equilibrium process. So that this is indicating that if X amount of emission is going from the donor side, the same amount of emission will be received in the acceptor end. And that is the reason behind arising this isoemissive point. This isoemissive point is very interesting here and indicating this is a thread. And now if we look into fluorescence lifetime profile, we measure in TCSPC, we found that donor emission is quenched at the cost of rising is coming in the acceptor's emission. This rising indicating again the thread is taking place. So now next we did time resolved emission spectra in steady state emission spectra, that is a equilibrium process. But now we see the emission process or emission spectra at different time. So that is possible in a CSPC instrument, and with some post-treatment of the lifetime profile, we can able to generate the emission spectra of the molecule at different times. So now I basically plotted the emission spectra of donor acceptor pair at different times, starting from 0.1 nanosecond to 1 nanosecond. So this is the rhodamin 6G portion, and this is the quantum dot. These two peaks are very closely spaced, and it is very difficult to separate these two peaks. That's why the thread study in this system is very challenging. Now we found that as time progresses, this portion emission intensity of this portion quantum dot portion decreases, but at the same time the emission intensity of rhodamin 6G portion increases. And again we found, like steady state in time resolved study also, there have been an isoemissive point, and this is indicating this thread is going up. Now the question is, since these two peaks absorb emission of acceptor is so closely spaced, how one would study the quenching process? So when the donor peak acceptor interfere that. So what we did, we basically splitted this individual spectra using a binomial curve. And what in binomial thing, we fixed the peak position one corresponding to 60 and another quantum dot, and then we splitted it one spectrum to two spectra, and in two individual window, we basically plotted all the spectra as a function of time. And this portion corresponding to the quantum dot portion, and this is corresponding to the rhodamin 6G portion. You will find as time progresses, the emission intensity decreases. Here it is increasing. Now, if I plot area under curve as a function of time, we'll get this kind of decay curve for quantum dot and a rise curve for rhodamin 6G. Why rise? Because the intensity of rhodamin 6G increases. Now, that as we increase the concentration of rhodamin 6G, or if we decrease the quantum rhodamin 6G, your thread time scale will be faster. This is obvious because when you have large number of acceptor around the donor, then it will be more efficient. We found this at different ratio quantum dot is to rhodamin 6G of thread time scale. This is 1:2, and when it is 1:2, your thread time scale is become shortened. So the next step is to finding the donor acceptor distance, because we know thread is used as a molecular ruler. So obviously, it is a common interest to measure the donor to acceptor distance from the thread time scale. And using this equation, this is the case that rate we can get it from quenching ratio, and tau rate is the time scale, the time scale, and R0 is the foster distance calculate theoretically using this equation, and RDA is the donor to accept a distance, that is our interest here, and we'll measure this one, and tau 0 is basically lifetime of donor in the absence of acceptor. And we found from this time component is corresponding to a distance 3.8 nanoseconds, 3.10, 0.4 nanosecond. But the thing is that from the table we found the this core of this quantum dot without this capping layer, that is around little more than 5 nanometers. So the radius is around 2.3 nanometer. And we found from DFT calculation that size of a rhodamin 6 is a radius around 0.7 nanometer. So now if I add 0.7 and 2.3, so it is not, it is coming something not equal to 3.8. So we are assuming that this molecule is basically embedded deep inside this capping layer. So this is not neither in the interface nor in the very core portion of the quantum dot. So this is fluorescence correlation spectroscopy. From using this from time measurement, we cannot get the hydrodynamic radius or hydrodynamic size, because core will only give this semiconductor portion, the size of the semiconductor portion, not the capping layer. But if somebody wants to know the entire size, including the capping layer, he should study this fluorescence correlation spectroscopy. So fluorescence correlation spectroscopy is a simple method. And from this curve, after treating, we can get the translational diffusion time of the molecule. And now using Stokes equation, we can from the diffusion constant. So these are the diffusion constant, and from there we can get the size of the molecule. And here we get the size of the molecule, and we found also the length of the capping agent from here, and we found the capping agent length, the hydrodynamic length 6 nanometer. We found the hydrodynamics means the entire molecule, but in this semiconductor portion obtained from the time measurement is around 5 nanometers. So the length of this one is capping agent is around 1 nanometer. So I also calculated the plate efficiency using lifetime steady state measurement, and we found a different pointer concentration, acceptor concentration, and we found that there is a nice matching between the steady state and time reserve. This is indicating that in the lifetime measurement, we almost detected 100% Fred. So dependence, temperature dependence also, if we increase the temperature, we found that the emission peak position of the quantum dot, that is donor, is shifted to the red side. And now it's shifted to the red side, so this is at different temperature. It's showing basically the emission spectrum of quantum dot, and you found, and this is the absorption spectrum of quantum dot, and you will find that the extent of overlapping between donor emission with acceptor absorption is decreasing in the, and that can be obviously and from 420 nanometer. So it was publishing chemistry. Because I already finished my time, so I just to present this. So very important. So recently you will find there is a surge in carbon dot field. The papers are publishing. So I found up to 2016, there's an exponentially increases number of paper published per year. But there is some problem with carbon dot field, because most of the author did not purify the sample with more scientific way, that causes some apparently interesting observation. But later we found that all due to the artificial carbon dot is not that interesting. So why people started using or studying carbon dioxide? Because carbon dioxide is non-toxic, water soluble, stable, highly fluorescent, and this is a carbon allotropy, and people have interest in carbons. Obviously, this is well accepted in the community. The second point is one can easily synthesize this one using facile one-pot synthesis method, and the most interesting property of this carbon dot is excitation dependent emission. So you can generate any emission wavelength at your choice by changing the excitation wavelength, and it has a very good application in LED or other photovoltaic devices. Now we've found that this studying several literature, this carbon dot has a broadly it has two different portions. One is core carbon. Core carbon is formed by basically
Sir, can you hear me?
Yes, I can hear you.
Yeah. Sorry for the interruption, sir. Actually, we are running behind schedule, and I'm very sorry for that. And
No problem.
Yeah. So you have to finish it by 2 minutes, sir. 2 minutes.
Okay, sure.
Please don't mind, sir.
Okay. So it has like one carbon input, and outer surface it contains some caffeine, and this is the types I can skip it. So we size this carbon dot, and we basically through silica column separation, we could able to separate this carbon dot into two batches. And also this is the same image, and this is briefly showing you the separation method. And after the spectroscopic studies, and we found there is no, in the crude carbon dot sample, there is excitation dependent emission, but after careful separation of carbon dot to different batches, we found there is not at all any excitation dependent emission properties. So now I'm going to conclude. So excitation dependent emission of fluorescence carbon dot arises due to the ground state heterogeneity and several striking phenomena of fluorescence carbon dot, like excitation dependent emission, highly fluorescence, and breakdown of Casas rule. Everything reported in high impact journal is basically due to the impurity in carbon dot. I would like to thank everyone for my talk. So any question from the audience? Am I audible now?
Yes, sir, you are audible.
Okay. So yeah.
Unfortunately, sir, your network seems to be a little poor. Your voice was continuously breaking during your talk. Very unfortunate. Actually, we couldn't do anything about that. We can't do anything about network, right?
Exactly. This is not in our control.
Yes. Okay. I mean, as we are running behind the schedule, I will I'll request the audience to contact Dr. Ghosh. If they have any query through his personal email, because we have to carry on. But let's please thank Dr. Ghosh for his keynote, such a wonderful keynote address. Now we will continue. Sir, can you just switch off your presentation mode, I guess?
Yes, sure.
Yeah. Yes, sir. So yeah, so we'll go into the talk. So our next talk. So now this talk will be about the talk or discussion on the topic. And our next talk will be given by Dr. Ravikiran Saripalli. He's a friend of mine, and he's currently a postdoctoral fellow in the Department of Quantum Information and Nonlinear Optics in Tulane University in USA. He has done his master's from IIT Guwahati in physics, followed by a PhD for 6 years in Indian Institute of Science, Bangalore. And then he had been a postdoctoral fellow for 3 years in PRL, Ahmedabad, India. He has published research journals, almost 6 with 12 conference proceedings. He's currently been a member of different scientific societies, starting from OSA, SPIE, IEEE Photonics, and he is working in a project funded by Defense Advanced Research Projects Agency, DARPA. Today, he is going to talk about the manipulation of light through interaction with nanomaterials. So please, ladies and gentlemen, welcome Dr. Ravikiran Saripalli. Ravi, over to you. Ravi, are you there?
Ravi is mute now.
Ravi, if you are mute, you just have to unmute yourself.
Yeah. Hello, everyone. Thank you. I would like to thank the organizers, Narajole Raj College, for inviting me to be part of this and give a invited talk. And it's really encouraging for young researchers like us to be able to share our research in front of such a large audience. And thanks, Abhijit, for inviting me. Basically, laser light is really important in the field of nanomaterials. I hope everyone's able to see my screen.
Yeah, you can make it full screen.
Yeah. Okay, so laser light is very important in nanomaterials. We can take this in two ways. The first way is in fabrication of nanomaterials, in study of nanomaterials. As in the previous talk, we already see that like in characterization, you use laser spectroscopy to try to characterize nanomaterials, and in fabrication, you can use laser ablation for fabricating thin films and lithography techniques to fabricate other nanostructures. But the other part of how laser light is important in nanomaterials is how light is manipulated by the use of nanomaterials. And by this, we mean light has many properties like wavelength, spatial structure, polarization, and many other different properties. And how nanomaterials are being used to manipulate light is also a very important topic as of now. But due to the time constraint, I'll be only talking about how spin and spatial structure of light is being manipulated using nanomaterials. And before I start, I would like to acknowledge the group members of, so this is a work that was done in PRL, Physical Research Laboratory in Ahmedabad. And these are the members who are involved in this work. And this is Professor Gautam Samanta, who is heading the group. And the work was done in collaboration with the Nanophotonics and Metamaterials Research Group in Tech. So light has angular momentum in the form of spin angular momentum and orbital angular momentum. So the spin angular momentum arises from the polarization of light, and this is easily observed in the lab by using a quarter wave plate, which are commercially available. And light also has orbital angular momentum, and this arises from the helical wavefronts. So these have a lot of applications, which I'll come to in the next few slides. And so you generally use a spiral faceplate or a spatial light modulator to be able to generate beams with orbital angular momentum. So what these beams have is a varying phase profile, if you can see my cursor. So, and it has different topological charges. So if you have L equal to 1, your phase is varying from 0 to 2 pi in one cycle. Whereas if you are L equal to 2, your phase is varying from 0 to 2 pi twice in one rotation along the azimuthal direction. And because the phase at the center is not defined, you have these in donut-shaped beams, or you have an intensity with no intensity at the center because the phase is undefined, or it's called a phase singularity. So this is not a very old field, maybe just 2 decades back. The first observation of orbital angular momentum was observed. So these are just another mode of laser light which satisfy the wave equation. And so there are different modes like the LG modes and the Bessel modes and the Airy modes. We'll be just talking about the LG modes. Why? Because they have a lot of applications, maybe also in like nanomaterials. So people recently STED microscopy has come into a lot of application in nanomaterials, where you are able to like reduce the diffraction limit that you have of a laser by using a beam with a donut shaped beam, or the same thing as an OM beam. So now you are able to reduce your diffraction limit, and you are able to image 1 micron particles, whereas a confocal microscope cannot image such clarity. You have a lot of applications in multiplexing and in communication using OM beams, because all these OM L1 or L equal to 1, 2, -1, -2 all represent orthogonal modes, and you can, on the same communication channel, use different modes to communicate your so your bandwidth of the channel increases to almost infinity. Not physically, but ideally that's the case. And also, I will show in some of the next slides how OM beam can be used to manipulate particles as well. So, as the first slide was about spin angular momentum and orbital angular momentum. In most cases, your spin angular momentum and orbital angular momentum represent two independent degrees of freedom. But when light interacts with certain kind of materials, then you start seeing spin orbit interaction, and these are very interesting. You start seeing spin orbit interaction when you focus light into birefringent crystals. When you go in with circularly polarized light, you start seeing orbital angular momentum transfer from spin angular momentum. These are observed in anisotropic materials or in inhomogeneous materials where you use meta surfaces, which are nothing but nanostructures, and you require very complex nanostructuring facilities for this. And I will come with a few examples of this. Or you can use Q plates, and also in isotropic and homogeneous medium, this is quite possible, but you have to go into the non-paraxial regime of light. That means that you have to tightly focus your light beam into these materials so as to see this kind of spin orbit interaction. So, as I said, you can use meta surfaces or nanostructures for seeing spin orbit coupling. So, just for example, if you design such kind of nanostructures, so these are plasmonic structures, which can be, mostly people use gold nanostructures on top of a glass substrate, and using lithographic techniques, you can fabricate these kind of structures. So, different polarization of the input beam act differently to such kind of structures. So if you come in with a polarization in this ES direction, your plasmon resonances will be in the direction which is shown in the blue arrow. But when you come in with a polarization in the EA direction, or the antisymmetric mode, your plasmon resonance acts differently. So basically, by just manipulating the input polarization to such kind of polarization structures, you start seeing various a manipulation in the polarization. And if you see a manipulation in the polarization, to conserve the total angular momentum, you start seeing a orbital angular momentum generation. So for example, in your transmitted beam, if you go in with the input left circular polarized beam, in the transmitted beam, you see a component of the left circular polarization and a component in the right circular polarization. But when it transfers from left to right, then you start seeing a phase term, and this represents the vortex generation or the orbital angular momentum. So when you go, so if left circular polarization is -1, right circular polarization is +1, then you see a OM of 2, a charge 2, topological charge 2. Similarly, there's another example where in 2014, Robert Boyd and Ibrahim Karimi's group in Ottawa have also shown this, where they have done lithography of such kind of structure. This is a 1 micron scale, and it's about 209 nanometers in length. And these are gold nanoparticles on glass substrates. Of course, you have a ENZ material also, or a ITO film in between. And you can see when you come in with different polarization, this is a COMSOL simulation. They have shown that your plasmon resonance is different, and because it has a spin dependent resonance, you start seeing these OM kind of beams. And that is what they show when you come in with a left circular polarized beam on this plasmon structure. The right circular polarized converted component will generate a orbital angular momentum. And this is the plot of the conversion efficiency. They were able to very efficiently generate a spin orbit interaction in these kind of materials. And the way to say whether it is a OM beam, of course, you get these donut shaped beams, but when you interfere with a Gaussian beam, you start seeing these fork kind of patterns. And by seeing the fork kind of patterns, you can tell the charge of the vortex or the OM beam. So next, in the spin orbit interaction, as I said, like you can also observe this in isotropic homogeneous medium, but you will need to tightly focus the beam, and this is not really possible in optics labs to go into the non-paraxial regime. First of all, we don't understand the non-paraxial regime to a great extent, and also it's very hard to generate non-paraxial beams. There was a work in 2017 where they have shown the efficient spin-orbit coupling in epsilon near zero films. And what epsilon near zero film is, if you take a simplistic brood model, then your dielectric constant depends on your frequency. And at a particular frequency known as a plasmon frequency, your real part of dielectric constant goes to zero. And this is known as the cutoff frequency or the plasmon frequency. And that depends on the number of charge carriers, your charge, and the mass of the charge carriers. For metals, this plasmon frequency lies, which is greater than optical frequencies. But for highly doped semiconductors, so with material science emerging so much, you are able to produce these highly doped semiconductors. For example, Indian tin oxide or zinc oxide kind of doped semiconductors. Then you start seeing that this omega p or the plasmon frequency comes into infrared, and these are wavelengths that we can access in the lab. So now when the real part of epsilon becomes zero, the light matter interaction is very interesting, because your real part of epsilon becomes zero. That means your refractive index becomes zero. So how does the light propagate inside, like inside such a medium? And you start seeing very exotic effects like high Kerr nonlinearity, vortex generation, which I'll be talking more about, and also tunneling of EM waves. I'll just get into those. So this is a tunneling of EM waves. So now, because your refractive index is zero, your wavelength in such a ENZ material, when you operate at that wavelength, is shoots up, and it's much larger, and so there are no diffractive effects. And so whatever electromagnetic wave you give to an epsilon zero material, it just passes through, or it just tunnels through. And this is very interesting, because such phenomena have never been reported before. And this was first observed in 2006, and there were other works which experimentally demonstrate this as well. And then high Kerr nonlinearity. This is a field in nonlinear optics where your polarization is input electric field, and your Kerr nonlinearity is a third order effect where your N2, which is a Kerr nonlinearity, is inversely proportional to the real part of epsilon, or the real part of refractive index, and so it also shoots up. I won't be going into too much detail, but you can definitely ask me questions on this later on. So this was the motivation of our work, to experimentally verify the simulations that people have done in 2017 to show this ENZ phenomena where you can see a spin orbit interaction. So that is what they do. They come in with left circular polarized beam, and the incident beam is a Gaussian. But in the right circular polarized beam, you can see that there is a OM, or an orbital angular momentum, which is generated. And what they show is, which is a remarkable result, is that you need to come in with an input paraxial beam, which is unlike any other case that was previously reported. You always had to come in with a non-paraxial beam to start seeing these in a spin orbit interactions. But here you come in with an input paraxial beam, and you start seeing this in spin orbit interaction. So let me explain this a little bit more. So here, this is the real part of epsilon. When it is zero, this delta is the term which tells us how much of the spin orbit interaction has taken place. And so when delta is large, that means more spin orbit interaction takes place. And so when real part of epsilon is zero, when you see that this is the non-paraxiality of the beam. So K perpendicular is equal to 0 means it is a paraxial beam. So in the paraxial regime, you start seeing spin orbit interaction. So for this work, two things are important. One is selection of the film, and also being able to generate this wavelength in the lab. So the film that we used is a ITO, or the Indian tin oxide film, and the carrier charge concentration was about 10^21 centimeters square, and the thickness is 310 nanometers. So you don't need really precise nano fabrication facilities. You don't need anything else. You just need to deposit films either by sputtering, RF sputtering, or laser ablation, and you're able to generate these kind of films. Of course, you need to manage the efficiency such that you attain large carrier charge concentration. And this leads to a cutoff wavelength of about 1240 nanometer. And now we have this film. So we also characterized it. We did a Drude fitting to the reflectivity and transmittivity, and saw that the cutoff is about 1240 nanometer. The real part of epsilon goes to 0. And now you want to generate this wavelength in the lab. So we did a second harmonic generation of a 2360 nanometer source, and you were able to achieve 1180. and we had a little bit tunability from 1180 to all the way to 1200 nanometer. And this work is still in progress. More details of this can be found in our publication recently. So these were the experimental setups that were used. So we used an ITF film. So an input beam, a PBS is a polarizing beam splitter, which converts your beam into horizontal and vertical component. And the horizontal polarization component is converted into spin orbital angular momentum using a quarter wave plate. So say we are generating left circular polarized beam that is incident into the ITO. The transmitted beam has two components. One is the converted right circular polarized beam and the unconverted left circular polarized beam. So we use again a quarter wave plate and a polarizing beam splitter to separate these two components. And the component which is converted, or the right circular polarized beam, has this vortex, and that you can see in the CCD. And of course, you also interfere with the Gaussian to be able to see that image on the CCD. And we repeated the same experiments in the reflected part as well. And as you can see, when you come in with the left circular polarized beam, in the right circular component, you see this vortex generation. The splitting of the vortex into two single charges can happen when a vortex beam is transmitted through a turbulent medium, and that is what we observe here. And when you do the interference, you can see these fork structures. So this is a topological charge 2, or a OM of order 2, which is produced. And when you switch the polarization, input polarization from left circular polarized to right circular polarized, you see that these forks flip. That means that the OM becomes +2 to -2, just to conserve the total angular momentum. Then we did some power measurements. With the angle of incidence, you see that the vortex generation is increasing, and it's a maximum at about 57 degrees. And this is consistent with other ENZ phenomena that people have observed, like the high KED nonlinearity or the super tunneling. Why this happens is because the dielectric displacement is continuous across the surface or the interface. And so you want to be able to maximize your transverse magnetic component of the polarization, and that happens at about this wavelength. And so that is what is happening here. And of course, when you increase the power of the input, your power of the vortex also increases, or the spin orbit coupling efficiency increases. And as we see that when we are going towards the epsilon 0, which is around 1240, when you are going towards that, your spin orbit conversion efficiency also increases. And still measurements are ongoing as to reach this 1240 nanometers, so that we see much higher spin orbit coupling efficiency. So this is the focusing effect. So when we are at the focus of the lens, you are in the non-paraxial regime. I mean, more towards a non-paraxial regime. But when you are very close to the lens, you are in the paraxial regime, and that is what they have shown. So this is a 20 centimeter lens. That is what we have shown. When you are at the focus, your spin orbit interaction and vortex generation is very low, and when you are away from the focus, then your spin orbit interaction is much larger. And this is consistent with the simulation. And we also did our own simulations using finite difference time domain methods, and that is a seam. This is a wavelength tunability at 1240 nanometer. You see the vortex generation or the spin orbit interaction is much higher, and this is consistent with our experiment as well. At around 60 degrees, you see that the spin orbit interaction is highest, and this is with different numerical aperture focusing. So when you have a tight numerical aperture focusing, that means it's a more non-paraxial beam. You see that the conversion efficiency is very less, but when you have a loose focusing, your conversion efficiency is much more. We did spectrum measurements. The total spectrum of the input beam is converted into the vortex, and so that means that this can be used for ultra fast measurements, and your pulse width also doesn't broaden too much. So this is a vector beam which has varying polarization across the spatial profile. That happens when you interfere a Gaussian beam with the vortex beam of having two orthogonal polarizations. And you can see in a vector beam, along the spatial profile, your polarization varies, and you observe such kind of lemon star structures as well. And we were able to simulate this as well, and we were able to generate vector beams as well as vortex beams through spin orbit interaction, and we were able to verify the simulation that was done in 2017. So with that, I conclude my work, conclude this talk. We have demonstrated spin orbit interaction and hence vortex generation using isotropic homogeneous medium without the requirement of high numerical aperture focusing, which was never done. And the vortex conversion efficiency will be much higher when we operate at 1240 nanometer, and this will be very useful for ultra fast vortex generation. We have presented this work in Clio, and we are submitting this work to PRL. I hope that it's a positive there. And I thank you all for your attention, and thank you to the organizers for letting me talk. This is my email address. Please feel free to contact me if you have any questions, and these are some of the publications that you can refer to in future. So, thank you. And if there are any questions, I'll be glad to answer if I have time.
Thank you, Dr. Saripalli, for his wonderful talk. We have time for just a few questions, one or two. If anyone in the audience wants to talk to him or have any questions, please unmute yourself and ask question. Those who want to interact with Dr. Saripalli personally, please note down his email ID. It's given, and you can interact with him personally.
Yeah, this is my email address. I can share this slide again. Thank you.
Okay, I guess now we have to carry on. Ravi, you have to please switch off your presentation.
I'm stopping sharing, and I'll mute myself as well.
Yeah, thank you so much, Ravi. So now we have to carry on. So now it's time for the next presentation. Our next presentation will be given by Dr. Udayanan Maiti. He is currently the Assistant Professor of the Department of Physics in Indian Institute of Technology, Guwahati, IIT Guwahati. He has done his Masters from Jadavpur University, followed by a PhD in Jadavpur University, after which he has done a BS Fellowship for 1 year jointly in Jadavpur University and Cologne University. He has been a postdoctoral fellow in KIST, Republic of Korea, followed by 1 year research fellowship in Institute of Basic Science, Daejeon, Republic of Korea. He has more than 60 journals, he has won patents, and he has got lots of prestigious awards like IBS Outstanding Awards, Young Scientist Awards, he has signed at JRF. He has also obtained a gold medal in Vidyashagor University in 2020, etc. And today we will be talking about graphene. The title of his topic is 2D atomic in graphene. So, ladies and gentlemen, please welcome Dr. Udayanan Maiti. Sir, you can start your presentation and you can unmute yourself.
Thank you very much for your introduction. Here, let me just a moment. Yes, I think my presentation is visible, right?
It's opening. Yeah. You have to make it full screen, sir.
Yeah, I have done it. Is it okay?
Yes, sir.
Is it visible?
Yes, sir, it's visible. Your presentation is visible, sir.
Yeah.
Just kindly make it full screen.
I have done it already.
Okay. Maybe it's coming. Okay, sir.
Yeah.
Yeah,
I think it's, yeah. So thank you very much for your introduction. I'm Udayanan Maiti and belongs to Department of Physics. Today I'm going to discuss about two-dimensional atomic layers and graphene and beyond. And considering that there are significant number of students from college students are there as a participant, so I'll try to make my presentation a bit non-technical, so that, but still if you have any question and concerns in any other sections, you can just stop me or ask me, or even you can ask just after my presentation. I think that many of you are already aware about the graphene. So what is the graphene? Is nothing but a single layer of graphite. So because graphite we used to use from our school days. So in a graphite, if you see that what are the atomic arrangement within the graphite, you can see that it is consists of different layers of two-dimensional layers of carbon. Each and the individual layers are known as the graphene. And individual layers are actually connected or have an interaction of Van der Waals type interaction. As a result, graphites are soft, so we can draw with some pencils. And when we draw with a pencil, few layers of such graphene comes on the paper, on our paper. But these are the few layers, 100 layers or 200 layers. But is it possible to separate a single layer of graphene? So initially, the scientists thought that it is completely impossible because a two-dimensional material is thermodynamically unstable. So every material try to make the energy as minimum as possible. So if you have a collection of atoms, so they will try to make some shape, it's a spherical shape or the other shape, not the two-dimensional shape. So it is thermodynamically predicted that it is impossible. Then there is a sudden discovery by these two guys, the Novoslav and James. What they have done, they have actually separated a single layer of graphene just by making the Scotch tape. Just took some graphite powder and used some tape and repeated attaching and deattaching makes this, they have successfully separated single layer of graphene and they got the Nobel Prize. And of course, they got the Nobel Prize not for just separating a single layer of graphene, but they have also given some interesting and unique properties of graphene which can change the perspectives of the material science and perspectives of the next generation electronics. It has that power. So, but when it comes to the case of graphene, when we need the graphene in large scale, like in a kilogram scale or ton scale, when it is application is a different bulk scale application, then you can easily think that it is impossible to separate some 1 ton of graphene from just by Scotch taping. It is impossible. So people have found that there is a simple technique. They just took the natural graphite and they just want to reduce the van der Waals interaction between the graphene sheets. So how to reduce the van der Waals interaction? Because van der Waals interaction depends on the distance. If you can increase the distance, van der Waals interaction becomes very less. So what they have done, they have made some chemical treatment and attached some functional groups over the graphene planes. And as a result, the distance between the graphene sheets increases a lot. And as a result, there is a very less van der Waals interaction. And even if someone do some handshaking, they can separate individual layers. But of course, remind you the fact that these individual layers are not graphene, but some functional group attached with the graphene. These are known as the graphene oxide. And there are processes of stripping of those functional group, and it is known as the reduction. So they can get the chemically converted graphene. It has certain functional groups, not fully removed, but still those functional groups, the residual functional groups, can also be used for the for any functional devices if it is customized according to the requirement. Now let me come to the what are the unique properties of graphene. So this single layer of graphene, this is 300 times stronger than steel, and its mobility is huge. You can see there is 200,000 centimeters square per volt per second. So it is a huge mobility. So electron actually moves like a bullet, and it has a ultra high specific surface area of 2,630 meters square per gram. That means if you have a 1 gram of graphene, you can cover an entire playground. So those properties actually people want to use for specific particular application. Not only these applications, there are other unique electronic properties also which people never seen before. Like if you consider that what the graphene is nothing but a hexagonal array here. It is the lattice is like that, and here all the atoms are carbons. But still you can see that within the lattice, I have actually denoted the two types of carbon, in two different colors. But why it has been denoted in two different colors? Because although all the atoms are carbon, But from the perspectives of the Bravais lattice, all the atoms does not have the same environment. If you see the blue atom, the atom actually shown in blue, you can see that there is an atom on the just right hand side. But if you consider the atom which is shown in the other color, you cannot see, you can see the atom on the left, not in the right. So there are all the carbon atoms, but their environments are different. Although they are connected with 3 nearby carbon atoms, but the connections, the orientation of the connections are different. So it's known as it has 2 sublattices. One sublattice, 2 sublattices are denoted in 2 different colors. And importantly, those 2 sublattices are equivalent because both are carbons and their arrangements are similar, only orientations are different. This gives rise to the unique electronic structure which people never seen before. That is you can see here, there is a valence band and conduction band, and valence band and conduction band touches at certain points. These are the K and K prime points in the K space. That means it is neither a metal, neither a semiconductor. Here, the conduction band and valence band just touches each other. So it's you can call it as a zero band gap semiconductor. This is a critical situation. And not only that, if you see the band structure close to any of the K point, any of the points where it touches the conduction band and valence band touches each other, these are the Dirac points. And close to the Dirac point, you see that the relationship, the dispersion relation, that means its energy versus momentum relation is linear. This is a unique one. And also, these are known as the valley degeneracy. That means if you switch from one such valley, one such Dirac point to another Dirac point, although it's yeah.
One small interruption here. Your presentation mode is on. Please switch on your presentation mode because someone from audience came in with the presentation mode.
Okay.
Please,
Yeah, someone interrupted. Your presentation mode has gone, sir. You have to manually switch it on again. Sorry for the interruption.
Oh. Is it okay?
Yeah, it's coming, sir. Yeah, make it full. Yeah.
So here, importantly, the dispersion relation is linear. That means the energy versus momentum relationship is linear. The unique features for graphene, and of course there is a valley degeneracy. That means the 2 valleys, the 2 Dirac points, the K and K prime points, they are, although they looks the same, but they are non-equivalent points. So if you just take an electron from one valley to another valley, it represents a different state. It's like for the case of electron spin, up spin and down spin are there. These are the 2 different states of spin states. Here, if you take an electron from one valley to another valley, this represents the 2 different states of electron. This is known as the valley degeneracy. And also the density of states at the Dirac point is 0. Density of states means the number of chairs for the electrons. Okay. So that means the electron can sit in different electronic states, but close to this Dirac point, the electronic states are very low, and at the Dirac point it is 0. So this is also a unique features which is very different from the 3-dimensional materials which people already knew. And those properties actually people now adopted to design different devices. And also there is a unique features which is related to the low density of states near to this Dirac point. That is, you see that if you make a capacitor, one side of the capacitor is the metal and another side is the graphene. And if you just, what you can see that the capacitance not only determined by the epsilon 0 A by D. You know that for a parallel plate capacitor, it is actually the epsilon 0 A by D is inversely proportional to the distance and proportional to the plate and the dielectric constant in between. But in this case, there is some additional term which is shown here within a bracket. This additional term is appearing due to the finite density of states, very low density of states near to the Dirac point. And just give you an analogy why this is happening here, you can see on the right side, this is a classical capacitor. And classical capacitor, there are a huge density of states near to the this edge of this band, electronic band. Now, if you apply the voltage, what will happen? So the mu, that means the chemical potential of one will go higher and the chemical potential of the other will go lower. And there is an exchange of electron from one side to the another side. But due to their high density of states, the electronic level will not change. It is similar to the fact that suppose you have two buckets of water, and if you take the water from one bucket to another bucket, 100 ml, the water level will not change. This is like a classical capacitor. Okay, only the height of the bucket matters. But in the case of graphene, it is one side, the density of states is low, so it is equivalent to, you can think of the one side, the graphene side is just a measuring cylinder. And the metal is just like a water bucket. So if you take 50 ml of water from the bucket and give the same amount to the cylinder, the water level in the cylinder will change a lot. So it is related to the fact that the density of states of the graphene is low near to the Dirac point, and this gives rise to the change of its intrinsic chemical potential. So these are the unique properties people applied in different areas of applications. Here I have listed some of the applications like solar cell, batteries, supercapacitors, high-speed transistors, and EMI shielding, and automatic automobile, airplane components. So a lot of, you cannot right now find any field which has not been touched by graphene. So in any field, the bioimaging, in every field, graphene is there. Here I would like to emphasize on some energy storage matters first, because this is the topic I have done my research most. So why the energy storage? Because you see that people are right now trying to go for the green energy, the renewable energy, solar energy and wind, but those energy are intermittent in nature. You cannot blow the wind on demand, and sun is not there in the night. So you have to store the energy. That means all those renewable technology must have some energy backup. You need some energy storage device, the battery or supercapacitor. Similarly, I think right now you are also using everyone is using the either mobile or the laptops, and for it requires some battery. That means you need to have a portable energy storage devices. And next generation cars are also electric vehicle cars. And for that, graphene is a good or excellent material for the energy storage. And I'm talking about electrochemical energy storage, where the energy stored due to the storing of charges on the surface of the graphene. Now, as I already mentioned, that graphene has a huge specific surface area. So if you can store your ions on the surface of the graphenes, individual surface of the graphenes, you can store huge energy within the same amount, suppose 1 gram of graphene. So, but there is a real issue. The issue is that because the graphenes are two-dimensional sheets, they have also strong interaction to restack back in terms of the graphite. Because people can make the graphene from the graphite, but the graphene again, they have a tendency to restack again to go to the graphite phase. And if they restack, then what happens that you cannot access the intermediate layer. You can just access the outer layers only. So how to restrict those restacking problem, which is a huge problem for graphene-based system in energy storage? There are different strategies. I have actually adopted some strategy which is known as the graphene gelation, and I started with some micron size sheets of graphene, which is dispersed in water, and by some simple methodology, I made them assemble on the interface. And when they assemble on the interface, metallic interface, and the water remains intercalated between the graphene sheets, so that I can reduce the restacking of the graphenes. And this particular material is very similar to the gel. Gel people use, you know that the contact lens, it is also a kind of gel. So similar kind of gel we have prepared from graphene, and this is very simple. We started with some metal plate, this just dipped into the dispersion of graphene oxides. And if you want to know the very detail, you just follow the this reference which we have published here, and you can see from this image, ACM image, where this is written as 5 micron, you can see that the individual graphene sheet, there are many pores in between. That means there is no complete restacking of the graphene. By this strategy, we can actually reduce their restacking, and we can of course control the orientation of the sheets by some tuning the gelation conditions, and then we used it for the supercapacitive energy storage, and we have found that it is actually it can be charged and discharged at a very fast rate. Within some millisecond scale, you can charge it. And of course, and the aerial capacitance is also very good. And this is, and with the increase of current density, you see that the 150 milliampere per centimeter square, this is at this rate, if we can charge or discharge, still it maintains a good capacitance. So it means that this is good for ultra fast charging of the capacitors. These are some metrics we have compared with the very excellent other papers. And there is a modern flexibility demand as well, because the electronic components, they are going to be more flexible. You can find the flexible display, all that. But for all those electronics, you need to have some power backup. But most of the power backups are rigid one. The battery is rigid, battery is not flexible. How to make it the flexible energy storage devices? We have used the same for flexible energy storage devices. And this undistorted curve at bending at different angles also shows that we can use this as an energy storage device which is bendable, and bending does not cause any harm to the performance. And next, I am going to just present a interesting topic, that how to tune the electronic properties of graphene. So graphene is made up of carbons, but if you replace carbon with some other heteroatoms like the nitrogen, sulfur, phosphorus, so that you can change the electronic property locally. And depending on their dopant site, where the individual atoms are, the dopant atoms are, they have a different arrangement. You can see that here my atoms is there, it is connected with 2 carbon atoms only. But if it is here, it is connected with 3 carbon atoms. This is known as the graphitic nitrogen, whereas here this is known as the pyridinic nitrogen. And if it is connected with the 5 member cycle, it is known as the pyrolytic nitrogen. So depending on the different configurations, their electronic properties are also different. But suppose this is, I have given the example on the basis of the nitrogen. But what will happen if you want to incorporate some elements which has a large atomic radius, like sulfur? If you want to incorporate it, so what will happen? Due to its very large size, it is hard to incorporate within the lattice site, because it will create a lot of strain, so it is impossible to. But you can see that at the edges where there is some defects, if we have some pores or defects, here even if this atom has a larger size, there is no issue. So we took this as some kind of theory by which, if we can create some pores, we can incorporate some big heteroatoms. But how to create the pores within a graphene? So we started with graphene oxide, And graphene oxide, as I mentioned, this is a functionalized form of graphene. But then there were already reports that in a graphene oxide, there are some patches, a region where there is no functionalization. This is graphene-like. And there is also some patch here. This is functionalized. So this is a percolated network of graphene and functionalized graphene. Now we took this as in some information, important information, that because it has a two percolated region, so if we heat it, the graphene oxide, then we can expect the two different regions due to their two different chemical structures. They have two different burning points. So we control some temperature, 440 degrees Celsius, and found that those functionalized regions, those are most disordered region, they burn first. As a result, we can create some holes within the graphene plane. These are the holes, and very tiny holes we can create. And once we create the holes, now it is easy to dope with the bigger heteroatoms. We have doped with the sulfur, and those sulfurs are mostly incorporated near to these pores because they are because we have confirmed it from the XPS that the configurations of these sulfurs. And we have done also density functional theory simulation. From that, we have found that due to this heteroatom doping, there is a redistribution of electron and the spin around some atoms around the edges. So this redistribution, localization of electrons has some impact on the catalysis. We used it for the oxygen reduction reaction catalysis. If you would like to have the more detail, please go to this publication. And with the same, we started another strategy where how can the dopant site in a graphite lattice?
Sir, sorry for the interruption. Actually, I'm sorry to say that we are running short of time. So you
okay.
Next 2 minutes, sir.
Okay. So here we have actually we did some dopant specific unzipping. This is a carbon nanotubes. When it is unzipped, when it gives rise to the nano ribbons of graphene, and this is the specific process by which we have done it so that it remains crystalline in nature. So it is very different from the other reported methods where there is a lot of disorder. You can see that from the TEM image, the crystallinity atom there. From this atomic resolution image, we have also confirmed that crystallinity is there. And from this XPS spectra, we have also seen that the unzipping happens mainly started from this pyridinic nitrogen, so that in the XPS after the unzipping, there is no pyridinic peak. And this is the mechanism of, I'm not going to detail of this mechanism of unzipping. And we have also done the doping of the graphene, where because it is a surface only material, anything put on the graphene, it can change its electronic properties. We have actually given the two different polymers in the two different regions to make it a PN junction diode. And because from the success of the graphene, people have started with exploring other 2D materials which are analogous to graphene. They have different properties. Here there is some list of some 2D materials: graphene, boron nitride, silicene, and the molybdenum disulfide. Particularly out of these, this is actually currently dominating in the field, which is known as the magazine. It's a delaminated titanium aluminum carbide. This is also 2D materials, but it is conducting. You can think of it as a conducting metallic sheet floating within the water. And this is the monolayer of MOS2, where you can see that in the bulk phase it is a indirect band gap semiconductor, but in the case of when it turns into the monolayer, this is a single layer, it's changed into the direct band gap semiconductor due to there is a removal of the interlayer coupling. With this, I would like to thank, and this is my mail ID. If you have any question, you can drop me a mail. Thank you. Thank you very much.
Let's all thank Dr. Maiti for such an interactive session, such a nice session. We have time for maximum 1 or 2 questions. If anyone wants to ask, please ask, because we are running short of time. We have to carry on. Those who want to interact with him personally, please follow his email ID. If there is no questions, let's thank Dr. Maiti once again for such an interactive talk. Sir, you have to
Thank you very much.
switch off your presentation mode.
Yeah.
Thank you so much, sir. So now I'll go to the last invited talk for today. And the talk will be presented by, again, a friend of mine, Dr. Kollol Roy, who is currently a research fellow in the Center of Advanced 2D Materials, located in the National University of Singapore, NUS in Singapore. Kollol Roy has done his MSc, particularly integrated PhD in Indian Institute of Science, IISc Bangalore, followed by a 6 year of PhD. After that, he has been a research associate in Indian Institute of Science in Bangalore. Kollol Roy has published 6 research journals, very prestigious journals like Advanced Materials, Nature Nanotechnology. There also has been work experience in Western Digital Bangalore R&D jobs. So with this, let's welcome Dr. Kollol Roy, and he will be talking about photons, plasmons, and nanometer size gaps. Kollol, over to you. You can unmute yourself and start presenting.
Hi, am I audible, Apradeep?
Yes, absolutely, Kollol.
Okay, I'm just. I believe the screen is visible.
Yeah, it's coming. Yes, Kollol. Make it full screen. Yes. Make it full screen. Yes, perfect.
Okay, thanks Apradeep, and thanks Professor Tapanendu Kamlia and other organizers for inviting me into this seminar. I'll be talking about photons and plasmons in nanometer size gaps. Basically, I mean, by now I believe it's clear that nanometers offer various interesting phenomena various interesting physical phenomena, and also it offers to control various physical parameters. That's why these are interesting. And in the context of photon and plasmons, I would also like to, in the context of photon and plasmons, I'd like to show that how nanometer size gaps can offer interesting stuffs. These are the outline of my talk. So first I'll talk about the motivation, like why these kind of studies are important, and then basic physics, and like which is very much metal permittivity, and then there will be few nanoscale devices, specific nanoscale devices, where will show that how photon and plasmonic responses are controlled, and then some examples of applications will be shown, and then at the end, just with only with very few slides, I'd like to show what we are doing in this field in our group in NUS. So that is this part, which is electrically controlled on-chip plasmon emissions and detection. That is the last few slides. Otherwise, it's a general talk in terms of photons and plasmons in nanometer size gaps. The motivation. So let's see what is light and what are plasmons. So light is basically electromagnetic wave. It's an which oscillates at very high frequency. We call it optical frequency. And whereas plasmons are basically plasmons are basically oscillation of free charges in metal, it can occur inside the bulk of a metal, but the most interesting part is when it occurs at the interface of a metal dielectric. So this is the main part of it that I'll be talking about. And one interesting thing that I should point out is, so when we are talking about plasmons and metal dielectric interface, then the electric field in the Z direction basically changes. I mean, how it changes in the Z direction, it's shown in this graph, where you can see that on the upper side of the metal plane, it extends around, say, 100 nanometer length scale, whereas inside the metal it extends around, say, 10 nanometer, 10 nanometer region. And so these length scale, I'm catching your attention by these red arrows are important because these are the length scales which basically tells us that nanomaterials can be interesting because electric field will interact only in this length scale if we are interested inside metal or outside metal dielectric interface. And these are few example of a different type of metal dielectric structures. You see that this is metal dielectric single interface, whereas there are like two interfaces. Whereas this yellow is basically the metal, and this light green shade is basically dielectric. And then various types of devices are realized just to facilitate these fundamental just to optimize this, just to facilitate light matter interactions by controlling these length scales, keeping these length scale in mind. And one more quick thing is basically I should also point out is light and plasmons are completely different in terms of as far as the nature of energy are concerned. So light is, as I already mentioned, it's electromagnetic wave, whereas plasmons are electromagnetic waves inside a metal. So the dispersion relations are different. So in principle, from light to plasmon, one has to go via some change, go via changing the momentum vector. So in short, if we summarize, what are the advantages and disadvantages? So light, photons basically offer diffraction limit. Photons are diffraction limited, whereas plasmons can go beyond diffraction limit. Photons are low loss things, whereas high loss happens in plasmons. Low interaction generally are observed in photons, whereas in plasmons strong interactions are observed. So and in terms of in terms of devices which are operating at optical frequencies, so these are the kind of a chart where you can see the dimensions versus the speed has a connection. So photonics offer high speed, but at larger dimensions, whereas if we go to the nanometer scale dimensions, then we can have similar speed but with plasmonic materials. So just to go to now to the basic part, basic part, how the metal permittivity offers plasmonic response. Basically, what I'm just showing here is basically light is an electromagnetic wave, which I already told, and then it interacts with free electrons, which undergo simple harmonic motion, and then free electrons with no damping loss basically gives rise to negative but real permittivity. So whereas free electrons with damping loss gives complex permittivity. So these are the two important parameters: negative permittivity and complex permittivity, which are tuned via various types of devices. And basically, that is again reflected in this dispersion curve, where you can see that plasmons basically without loss, it basically follow a certain energy momentum relationship, whereas which is like curved, whereas photon is a straight line. And this comes from very simple understanding of Drude model, where you can basically if you write down the force equation, where electrons are placed inside an electromagnetic wave, it basically gives rise to this complex permittivity. So that is what I'm telling is important. If you want more information for the students, you can follow this book, which talks about the detailed evolution of this theory of metal dielectric theory. And basically, I mean, whereas here I'll be talking about more about the consequences of these complex. My laptop is stuck. So consequence-wise, when I'm coming again to the dispersant relation, so what you can see is basically, let's talk about, say, metal layer interface, the dispersant relation. Then what you can see is the same energy actually can have a different set of wave vectors, which is very large in value compared to the wave vector which light can offer. So these basically tells us that the wavelength of a plasmon can be very smaller in size, and hence it can be squeezed basically beyond the diffraction limit. So that is the beyond diffraction limit. That is one of the most important conclusion of metal dielectrics, of the property of metals. Which are used again and again in plasmons. Now, if I go quickly, if I show quickly what is, so as I was telling, is basically metal plasmons and lights are fundamentally different. So in principle, there are two different forms of energy. So you can't, so you have to go via a certain mechanism to go from one form of energy to the other. And this is basically shows one example of how they are excited. For example, say if we want to excite plasmons which are occurring at this metal dielectric interface, this part of the metal dielectric interface, which is coming over here, then we have to shine a light in a certain angle, which will connect via this metal thickness and excite this plasmon. So this is a momentum match phenomena, which are demonstrated over here, and definitely it depends on the thickness of the metal. So if we, that is because of this this part of the electric field we are utilizing, and if it is too thick, then we will not be able to excite the plasmons which are occurring in this thickness. So I'm just again talking about the basic nanoscale idea, like why nanoscale systems are important in terms of plasmons. Anyway, there are multiple such structures which can be used to excite plasmons, and it's not just a prism. It can be grating. It can be many other system like a scatterer, which and that also gives moment idea. So let's look at now few like control via specific device design in nanoscale. So this is one of the famous metal dielectric system which shows that the effective index can be controlled, and hence so for example, you see there is a dielectric dielectric rod which has a dimension of d, and then it is placed on top of metal by a gap of certain height, by a small gap which is filled by another dielectric, and then the effective index of this system, you can say you can relate to the permittivity also by effective index changes as you change the gap. Say for example here it's tuned from 2 nanometer to 100 nanometer, and hence effective index changes drastically. And what is the consequence of this index change? You can see it over here. It's basically, if you look at the bottom images, then at when the dielectric cylinder is placed much above the metal, then all the lights are inside the dielectric, whereas the moment you are placing it near the metal, basically light is interacting with the metal and getting focused. And you can see here also, here in this image, light is mostly residing inside metal dielectric interface. That is basically, this phenomena is represented by the mode area, which is basically effective area within which most of the energy is confined. And you can see the effective area, mode area, which is normalized by the area when it is not interacting with the metal plate. It can be like 100 times smaller when these dielectric and metals are placed only a small nanometer, few nanometer apart. And definitely it has a consequence. Is basically, although the light is getting confined in metal dielectric interface, there is a loss that has to that comes, and because of that, so you can see the propagation loss. So for example, is high. For example, if we take any particular D, say 500 nanometer, then the we compare it with different gap size of different age, say for 100 nanometer gap versus 2 nanometer gap, then you can see that the propagation length is very different. It changes by almost 2 orders of magnitude. So another example of such confinement, light confinement, is basically you can see you can achieve in metal interface. You can see in this graph is when there is a small. So in this graph illustrates different mode energy, plasma mode energy at a different gap size. So this is again, I should mention, previous one was metal dielectric interface, whereas this one is metal interface, which are placed at a small distance. Say for example, this one is 3 nanometer gap is there, whereas 30 nanometer, and so on. And you can see the effective mode energy, you can which is presented over here, are changing as we change the gap. As we make the gap smaller, resonance energy is increasing. So this is also another phenomena which is a consequence of light matter interaction at smaller gaps. This is another beautiful example where one can show that two metal nano structures which are bow tie in nature, that when they're placed one in front of the other, so electric field enhancement happens, and that gives rise to a physical phenomena which is the study of Rabi splitting. So Rabi splitting is nothing but energy exchange between two different state of matter, two different state of systems. So in this case, what is happening is, in this metal dielectric, in this metal interface, this metal interface is acting as a cavity which is storing one form of energy, and that is interacting with nanoparticles which are placed inside these gaps, and so that changes the scattering phenomena of light, and that is observed. You can see there is a deep scattering is less when the interaction is strong between the cavity and these nano dots. So this splitting is called the Rabi splitting. This is one interesting physical phenomena and very fundamental in many cases. Another metal interface, metal insulator metal structure, which gives rise to a different form of physical phenomena, which is light emission. So generally, light emission from a semiconductor is known, that is via spontaneous emission, jump from higher energy state to the lower energy state of matters. So in this case, what is happening is basically electrons are tunneling from via inelastic method from one metal to the other, and hence giving rise to emitting a light. So this is called inelastic tunneling phenomena, and that can also act as a light source. So you can see that density of states are very high when two metals are with sharp interface are placed very small distance apart, which is of the order of few nanometer only, 1 or 2 nanometer only. And quantum efficiency is getting higher, which is of the order of 1%, as also the dimension in the Z direction, which is the thickness of the cube, is changed. So I'll quickly show a few more examples in this context. So usefulness of this light matter interaction phenomena, which is a laser. So what happens in this case is a silver surface, and another semiconductor is placed with a small gap of dielectric. So this is a metal dielectric interface with a small gap, and then a mode confinement happens in the metal dielectric interface, because of which light amplification occurs. So you can see within the plane of the structure, light goes full internal reflection, total internal reflection, and facilitates lasing. Again, nanostructure plays another. So the lateral dimension of this device also play an important role, because you can see when the structure is changed from square dimension to a irregular dimension, the number of modes can be controlled. In this case, on the left side, we can see multiple peaks, whereas we can see only one laser, which is controlled by the dimension of the structure. Another classical example in the photonics, where light is coupled via grating into a plasmon, and then it is again taken out after some modulation. This is high-speed plasmonic modulator, which operates at very high speed, gigahertz and gigabyte speed. So what is happening, you can see, is basically light is coupled on the leftmost side, and it has mostly this type of nature as it and then it starts interacting with a gap, and then that is where modulation is facilitated, and ultimately it is taken out by the scatter by the So another interesting physical phenomena is squeezing light at very small gap, which facilitates mixing of frequency and photo generation. So photo mixing, which is a nonlinear phenomena that happens because light is squeezed so much that the electric field is now very intense, and hence simple harmonic motion of electron cannot be assumed any longer. So light now interacts non-linearly.
Sorry for the interruptions. Actually, we are running short of time, and 3 more talks are coming up. So you have to wrap it up by next 2 minutes. Sorry.
Sure. No problem. This is another example where you can show the switch formed by a light matter interaction. So that there are basically you can see, so there are 2 waveguides side by side placed, and then when a bias is applied, electrical bias is applied, then what happens, the effective index on the left waveguide can be different than the effective index on the right waveguide. You can see the effective index is low compared to the right waveguide, and hence the amount of energy that can be here is different, and hence you can control the path of light that it takes, either on the left side or on the right side. So you can see that no voltage applied. They have similar intensity on both sides. So light input is over here, light output is here. You apply a voltage, negative voltage, you can see the light is going only on the upper part, whereas you apply positive voltage, light is going only at the lower part. And finally, I'll quickly show what we are doing in Universe here. It's basically, it's a inelastic tunneling, which I mentioned earlier. It's basically, again, when light is coming from one electrode to the other by a small gap, then light can come out. Or another phenomenon can also happen is basically it can excite a +1 as well. So we take this, and then inside a metal MIM structure, density of states can be very high, and using this idea, we have finite plasmonic excitation. And this is one typical example where you can see that it's a gold electrode and then aluminum electrode, which are separated only by 2 nanometer, and then inelastic tunnel happens, and then that excites plasmons. And then the similar phenomena can also help in detecting the plasmon. So it's basically in one side you have plasmon source, on the other side you have plasmon detector. So the advantage of this is basically this is happening via tunneling, and hence it can be very high, it can operate at very high speed. This is basically the detection phenomena. On the left side is a modulation at the voltage input, and on the right side the detected voltage output. And we also understand the mechanism by which this kind of excitation is happening. Is basically we generate via MIM gap, and then that goes to surface plasmon via various pathways. And we control that. For example, in this phenomena, in this presentation, what we're showing is if we control the gold thickness, aluminum thickness, then so in one case we have a small aluminum thickness, and hence we have a specific type of SPP, whereas it's a specific type of SPP which is occurring at aluminum glass interface. And if we increase the thickness, then that surface plasmon is completely gone if we have larger aluminum thickness, which I mentioned earlier. So with all these, I'd like to thank you for your attention. And in terms of conclusion, so this is I already mentioned, and thanks for your attention.
Let's all thank Dr. Kallol Roy for his wonderful interactive session. Unfortunately, we don't have any time for interaction, so the audience, I would like to request you to contact Dr. Kallol Roy in his email ID personally if you have any questions regarding his presentations. Thank you, Kallol, for your wonderful talk.
Thanks, Abhudi.
Now, with this, our invited talks for today is concluded. So now this is time to carry on, and we'll go into the paper presentations. We have three paper presentations today. I would like to request the paper presenters to finish their presentations within 10 minutes because we are running really short of time. So our first talk will be given by Dr. Piyush Kanti Samanto from Kontai Prabhat Kumar College, and he is going to talk about electrical and optoelectronic properties of chemically synthesized zinc oxide nanoparticles. Dr. Samanto, you can unmute yourself and start your presentation.
Okay. Thank you, Dr. Pradip, for giving me, and also the organizers for giving me the opportunity. And am I audible? Am I audible?
Yeah, yes, sir. Absolutely fine. You can start your presentation, sir.
Okay. So, what I'm going? Is the PowerPoint is visible now?
Yes, sir. It's absolutely.
So I'll just discuss here in short the electrical and optoelectronic properties of zinc oxide nanostructure synthesized by a chemical route. I'm skipping these introductory parts. And as we know, it is a very popular material, zinc oxide, basically a 2,6 type semiconductors with high band gap. and the band gap is direct band gap, and it exhibits high transparency to visible window. It has an excellent piezoelectric property that can be used for green energy harvesting, and excellent luminescence property that may have potential applications in electronics and several biomedical devices. So with this brief introduction, I'm starting my lecture and I'm skipping the chemical synthesis part because this is a very standard protocol and that are available in literature. In brief, we have just used zinc acetate and lithium hydroxide, and by appropriate stoichiometric ratio, we followed the standard protocol for the chemical method and prepared the materials. I'm directly going into the results. The structural studies involved the X-ray diffraction studies, and here it shows the X-ray diffraction pattern of the synthesized material. Sharp peaks appeared over here that indicates the well crystallinity of the material, and we have indexed these peaks with and found the structure to be hexagonal, and these peaks indexing is quite consistent with the standard JCPDS. And from the diffraction curve, we can also calculate the crystallite size. In fact, by crystallite size, we mean here the coherent domain participating in diffraction of X-ray. And we used a Scherer formula to calculate the particle size, where this beta is the full width at hub maxima of the peaks, and theta is the corresponding diffraction angle. And we considered the highest intensity peak for this calculation. This calculation shows that the crystallite size is 16 nanometer, which is very small. And we also see that the intensity of these different diffraction peaks are different, which clearly indicates that the growth rates of various facets of the zinc oxide crystal is different. So we have studied here the degree of orientation, which basically the fractional intensity of a particular peak to the aggregated intensity of all the diffraction peaks, which shows these green bars are the observed data, and the blue bars, and the green bar shows the standard JCPDS results. The results are almost consistent except this 101 peak, that is due to the difference in the surface energy of this phase as per the reported structure. We also studied the impedance spectroscopy to study the different contribution of grains, grain-bound rays, and electro-electrolyte interface effects on the impedance of the material. So this graph shows the frequency dependence of both the real and imaginary part of the impedance. And these formulas are well established, so I am not going into details. And this figure shows that both this real and imaginary impedance gradually decreases with increasing frequency. So as we know, as we increase the frequency, obviously the space charge increases, which in turn reduces these impedances. It is also observed that the imaginary part of the impedance has a higher value compared to this real part. To understand the various contributions like grains, grain-bound rays, and interface into the impedance spectrum, we use the Nyquist plot where we have plotted the real part of Z and negative imaginary part of Z. We get a pattern sort of like this. So this pattern can be divided into two parts. One is this semicircular arc, and this is a larger arc. So the first part is responsible for the bulk contribution, and second part is for grain boundary. And we see that this arc is quite large. This indicates that the grain boundary has a large contribution in the electrical conductivity of this material. And from this semicircular arc, we can find the bulk resistance of the material. That is from the bulk contribution. That was about 160 kilo ohm. And ideally, this circle it should be ideal circle, the centered at this zero axis. But we see a depression of the curve due to non-divide type of relaxation procedure that can be incorporated by using additional constant phase element into the equivalent RC network of the dielectric system. So this figure shows the variation of the conductivity, AC conductivity with frequency. A plateau is observed in this low frequency region. It indicates that in the low frequency, the conductivity is almost frequency independent. But as the frequency increases around 10 to the power 4 onwards, then the conductivity goes on increasing. And beyond a certain characteristics frequency, again, it shows a saturated or lower behavior. And the DC conductivity can be calculated from these intercepts, and it was calculated to be 4.9 10 power -8 ohm centimeter inverse. To study the relaxation phenomena, we show here the loss tangent spectrum as a function of frequency, which shows an initial increase of the loss tangent to critical values up to 2.75 kilohertz, and it gradually decreases for higher frequencies. Now, this is because, as we know from the theory of dielectric polarization, that on application of an alternating electric field in dielectric sample, the dipole tends to oscillate with the frequency of the applied field. But beyond a certain frequency, the dipoles may no longer be able to follow the oscillations of the electric field, and the oscillations of the dipoles becomes out of phase and leading to the dissipations of energy. So this is how the energy dissipation occurs. And the relaxation time we found is quite low. This is 0.36 millisecond in case of our samples. And this was calculated from this graph. And this decrease in the higher frequency region may be attributed to the accumulation of space charge due to in the high frequency region. The optical properties of the material were studied by observing UV visible absorption spectrum and photoemission spectrum. This graph shows the UV absorption spectrum of the sample, which shows the low absorption property of the material. That means the material is quite transparent, especially in the visible window. And we can use tau equation to calculate the band gap from this UV visible data, where this alpha is the absorption coefficient and H is the band gap of the material. And for direct band gap, this exponent is half, that is here it is 2, and for indirect band gap this will be half. So as you know, the zinc oxide is a direct band gap semiconductor. We have used this equation, and getting the slope from the high absorption range, we can calculate the band gap to be around 3.52 electron volt. So this is the photoemission spectrum of the sample, which shows a strong photoemission peak peaked at around 582 nanometer. So usually, as zinc oxide has very high band gap, the visible emission, UV emission is the characteristics emission because of this high band gap, but it shows visible emission due to the presence of defects that may grow during the low temperature chemical growth. So here we see the emission peak, it shifts towards this towards 582 nanometer, and as there is no doping, so it is obviously due to the shallow level emission, that means due to defect states. And the defects energy states has been already calculated by many researchers, and from their data we can see that this emission can be correlated to the existence of some interstitial oxygens in the synthesized zinc oxide crystals. So in conclusion, we have successfully synthesized well crystalline zinc oxide nanostructures of woodite crystal with size 16 nanometer. It exhibits a non-Debye type relaxation process which induces an additional phase in the equivalent RC network of the equivalent dielectric model. And we observe a large grain boundary effects because since the materials is nano resin, so lots of grains are created. So grain boundary effect is quite high as it is expected, and loss tangent increases in the high frequency region due to space charge accumulation. And I have already mentioned that this optical emission is due to the oxygen interstitial. So here I end up my lecture, and I must acknowledge our college and the DSTP government of India for providing these measurement facilities in our lab. So thank you very much.
Thank you, Dr. Samanto, for such a wonderful talk and your insights on the novel characteristics of the zinc oxide nanoparticles. Let's carry on. Our next talk will be from the southern part of India, and it's the talk by Dr. M. Krishnaveni from Manonmanian Sundaran University, Tirunelveli, Tamil Nadu. So I would request Dr. Krishnaveni to start your presentation and to unmute yourself. Ma'am, are you online?
Sir, please repeat the name.
Sir.
M. Krishnaveni. Yeah. Ma'am, you can start your presentation.
Yes. Thank you for giving opportunity to present my work here. So I'm very thankful to organizers. I'm going to present my presentation on structural and textural characteristics of a nanoporous material and its catalytic application. Sir, my PPT is not supporting.
Now, are you presenting in smartphone or you are in laptop?
Sir, I'm in mobile phone. I'm presenting.
Okay, you will be able to see there is a button called Present Now, and from there you will
Actually,
be able to.
PPT is not supporting to me.
Okay, actually we don't have much time, so at least you can, if you don't have a PPT, you can't open it. You just briefly tell us about your novel work, about your.
Okay. Thank you so much.
Yeah.
Yes. So today I'm going to discuss about structural and textural characteristics of nanoporous aluminophosphate and its catalytic application. So in the investigation of the synthesis of aluminophosphate molecular sieve from simple method in presence of a low cost effect N-butylamine as template without autoclave. Generally most of the catalysts are synthesized by the help of autoclave. For that we have to need a large amount of pressure and the temperature. But in our method, there is no need to use autoclave like that. By the simple method, we synthesized aluminophosphate molecular sieve using an amine template. These catalysts, it is characterized by various spectroscopical techniques like XRD, IR, and surface area bed adsorption isotherm, and SEM, TGA, and TTG, etc. First, the characterization, it is XRD measurements. This indicates the molecule, the peak, it will be appeared in a low angle around 0.6 and 0.5 degree. This indicates our molecules to be crystalline nature of the material. The intensity of the peak indicates the molecule, the catalyst to be crystalline nature. And next, FTIR spectrum indicates the formation of a tetrahedral framework of mesoporous aluminosilicates. Then the thermal analysis, that is TGA. While taking this TGA, there are three weight laws occur for this catalyst. The first weight loss around 100 to 120 degree. This indicates the loss of water molecule. And the next weight loss around 270 degree and 330 degree. This indicates the loss of organic template molecule. After that, there is no weight loss up to 800 degree. So that indicates the molecules should be stable around 800 degree. And the bed adsorption isotherm indicates the molecule to be a nanoporous in nature, because the surface area for alpo is 90.986 and zinc alpo is 248.812. So both the molecules have the pore diameter is around 52 angstrom and 55 angstrom. This confirms our molecule to be nanoporous in nature. Nanoporosity of a molecule is confirmed in this method. And the scanning electron microscopy indicates our material, synthesized material, should be a crystalline nature, and the pores of molecular sieves, it is very thin. It seems to be the crystallinity of the molecule. And the EDX also confirmed by the presence of synthesized molecule composition aluminophosphate. And after that, the materials are synthesized and characterized. The characterization confirms the activity of the material. After that, the catalytic activity of the material is confirmed by the use of trans-esterification reaction. In this reaction, the synthesized material is used as a catalyst. We took used palm oil and ethanol. After that, the catalyst. So the trans-esterification reaction has taken place. Important parameters are fixed, that is reaction temperature, contact time, molar ratio, and catalyst dosage. After that, it is optimized. Our catalyst is around 50 degree and 2 hours, 1:3 molar ratio, 0.5 gram catalyst dosage. We could have a good biodiesel selectivity, that is nearly a 92.5% for alpo and 70% for alpo. So this indicates that our catalyst is to be very efficient for the synthesis of biodiesel from waste cooking oil, that is waste palm oil. So this is our uniqueness of the work. Even a 0.5 gram of catalyst dosage, we can synthesize from a waste oil into biodiesel. So the present strategy could potentially contribute to saving energy and time in catalyst and hold a significant promise for biodiesel production from used palm oil or used cooking oil. Thank you for your patient listening.
Thank you, ma'am. Let's all thank Dr. M. Krishnaveni from Tirunelveli, Tamil Nadu. So we have the last talk for today, and it's the talk again on zinc oxide nanoparticle. So let's please welcome all Dr. Vidyut Haldar from Damda Motichil College, and he will be talking about on positron annihilation studies on copper doped zinc oxide nanoparticles. So Dr. Haldar, you can unmute yourself and you can start your presentation. If you find any difficulty, please let us know.
Well, can you listen to me?
Yes, sir. We can listen to you, sir.
Can you see the slides?
Not yet, sir. You have to go to the right side at the bottom, present now button. You have to click it.
That I've done, and I've done it.
Then you just open your presentation. You just, at this situation, minimize everything and open your presentation.
Okay, I will go to the screen and share. Okay.
Yeah, share your window or entire screen, whatever. You click any one of them. Yeah.
Okay, can you?
Yeah, it's slowly coming, sir. Yes, sir. Yes.
Okay. Yeah. So, can I start? Okay.
Yes, sir. Sure.
Very good noon to all of you. I am Dr. Vidyut Haldar from Damda Motichil College, Physics Department. So today I am going to give a talk before you on the topic positron annihilation studies on copper doped zinc oxide nanoparticles. Okay, our objective was to incorporate defect-induced ferromagnetism in copper-doped zinc oxide nanoparticles. And why to choose zinc oxide? Because zinc oxide, along with magnesium oxide, titanium dioxide, they are oxide semiconductors, and it has a very wide band gap. Zinc oxide has potential application in room temperature magnetic semiconductors, optoelectronic material, magneto-optic devices, future generation solar cells, room temperature ferromagnetism, etc. Now, defects plays the most crucial role in magnetic and optical properties of zinc oxide. So, incorporating defects induces ferromagnetism in such system is a topic of intense research nowadays. So, by employing positron annihilation spectroscopy, these defects can be characterized. In our earlier paper, okay, in computational condensed matter, we have done some density functional theory studies on copper doped zinc oxide system in order to understand the changes in the electronic property in copper doped zinc oxide. And it has been found that copper atoms, when doped at cation sites, produces a significant magnetic moment along with half metallic behavior. In fact, two copper dopants have been doped at different zinc sites by varying the dopant distance. This is all done using density functional theory. And then before you, you have two pictures, two figures On the left, you have the pure zinc oxide system. You can see the density of state is symmetric, whereas on the right, you have copper doped zinc oxide system where you can see a bit of unsymmetric behavior out there. Okay, so that is exciting. So a brief conclusion that we had from DFT studies that we already did was that the total density of states for undoped zinc oxide matrix is totally symmetric, which suggests that there is equal number of spin up and spin down electrons in the pure zinc oxide system. However, in case of copper doped zinc oxide system, the total density of state is asymmetric that we already had. So partial density of state analysis reveals that 3d orbital of copper give rise to the asymmetry due to the presence of unpaired electron in the system. Ab initio calculation reveals that each copper atom doped at zinc site generates a magnetic moment of about 1 Bohr magnetron in the host matrix. The presence of unpaired electron of copper generates non-zero magnetic moment in the copper doped zinc oxide matrix. The value of the magnetic moment linearly increases with the increase in the doping concentration of copper atom. Thus, copper doping induces defects, thus showing ferromagnetic behavior. It has been observed that the band gap of zinc oxide decreases significantly on doping copper atoms at zinc site, which further decreases with the increase in copper concentration. So with this theoretical calculation behind us, we wanted to correlate with the experimental findings. Okay, and therefore we made some sample preparation by taking appropriate amount of zinc oxide and copper nanopowders to prepare samples of 0%, 2%, 4%, 6% of copper doped zinc oxide by weight and mixing them thoroughly, sintering them, and then using ball mill grinding, we have achieved particle size of about 8 to 10 nanometers. And then we are supposed to characterize the samples. So we did it using X-ray diffraction studies of all the samples were done to ensure whether the copper is properly doped at the zinc site in all the samples. UV visible spectra were taken to determine the band gap in our sample. Some positron annihilation measurements were done to study the type of defects and their relative concentration. So this particular study, the third one, is of importance in this particular topic, and it's still on because of the lockdown. We are unable to do a more number of measurements. And finally, we intend to do some magnetization studies using SQUID. Because our main emphasis is on positron annihilation, so to those who don't know about much about the positron annihilation, I'm just quickly going to tell you that positron, being an antiparticle of electron, annihilates as soon as it comes in contact with the electron, or otherwise it can also form positronium atom, where both the electron and positron, if they are in parallel spin, it is called orthopositronium, and if they are anti-parallel spin, they are called parapositronium. And then this positron atom once again annihilates and give rise to gamma rays. And then different mode of annihilations are there. So free annihilation has a different lifetime from positronium annihilation, and so this particular chart I'm not going to really talk about much. Here, in positron annihilation spectroscopy, basically it involves 3 different techniques. The positron annihilation lifetime spectroscopic measurement. Okay, the second one is Doppler broadening of annihilating radiation measurement, and the third one is angular correlation of annihilating radiation measurement. Out of these, first 2 are common. The third one is not as common as that. Okay, so in a positron annihilation lifetime spectroscopy, we take sodium-22 as our positron source, which gives rise, emits positron and has a half-life of 2.6 years. As soon as the positron is emitted, it comes through the excited state of neon, which has a very small lifetime of 3.7 picoseconds. This excited state of neon comes to the ground state of neon by emission of a 1.276 MeV. So this gamma ray, when it is detected, it announces the birth of positron because it can be taken almost simultaneously. Positron, after entering into the material or matter, okay, quickly thermalizes, and then it annihilates with the electron present out there. And in most of the cases, about 99.7% of the cases, this electron-positron pair annihilates and usually gives rise to 2 gamma rays, which moves in the opposite direction in the center of mass system. Okay, if one of these gamma rays can be detected, okay, so detection of one of these gamma ray gives or announces the depth of the positron. So by finding out the difference in the time between this gamma ray, detection of this gamma ray, and the detection of annihilating gamma ray, one can find out the lifetime of positron inside the matter. And for that, there are two detectors which are used to detect the two gamma rays, one for the birth and another for depth of positron. The source sample assembled is kept in between the detectors, then fast coincidence system is used, and then a time spectrum is taken, okay, using this, okay. So a time spectrum is taken. And this is a typical time spectrum, okay, and from this spectra, using computer analysis, using the computer program PATFIT88, least square fitting of experimental law spectrum, it is analyzed in terms of finite term lifetime components. Okay, usually 2 to 3 components are taken, and each of these components has their own interpretation. And in our present positron analysis, it is based on two-state trapping model, out of which the smallest component tau1 is due to positron annihilation in the bulk, and the longer component tau2 is due to the positron annihilation in the defect. And the positron lifetime in the blot state, it can be calculated using this particular formula from tau1, tau2 and their intensities. And therefore, in two-state trapping model, the tau2, the longer component, and tau-b are the physically important quantities. Doppler broadening spectroscopy actually measures the Doppler broadening in the annihilating gamma ray because of the momentum which is present with the electron-positron pair before the annihilation. As a result of that, the energy of the gamma ray, which is supposed to be 0.51 MeV, okay, gets broadened, okay, and this broadening depends on the mainly the momentum of the electron with which the positron is annihilating. So it depends on the electron momentum distribution and nature of defects and defect density in metals and alloys. This is a typical Doppler broadening spectrum, and you can see that there's a difference between a defect and a defect-free spectrum. And these wing parts are very important because they comes from the momentum of the electrons from the core. Okay, and mostly the positron like to go to those places which has defects. So from this spectrum and by calculating the two parameters which are known as the S parameter and W parameter, we are able to find our relative concentration of defect which is present and also the kind of defects which are there in the sample. Nowadays, we use coincidence Doppler broadening where both the gamma rays are detected and their energy spectrums are overlapped the two mutually perpendicular direction to get a spectrum of this type, and analysis of the central part can give a lot of information. So here you can see the two spectrum which has been obtained by a normal Doppler and a coincident Doppler. So in case of a coincident Doppler, the background to peak ratio is highly enhanced, and which gives a lot of information about the defect or type of defect which is present in the sample. And third one, which is not a very regular kind of a measurement, is called angular correlation. It arises because the two gamma rays in the laboratory frame may not go exactly opposite each other because of the momentum of the electron. And by measuring the angle of deviation in the gamma rays out of 180 degrees, we can calculate the electron momentum distribution in solids, energy band structure calculation in metals, and Fermi surface determination. Well, so positron annihilation spectroscopy depends on the electron density matter, most effective for relative measurement, study of defects, nature of defects, trapping behavior of defects in metals, effective in probing mean free volume, hole size, density, and distribution in polymeric material, is very sensitive to phase transition, and sensitive to external condition of temperature, pressure, and mechanical stress. So now coming back to our sample, we have taken the XRD for our samples, and these X-ray measurements or X-ray plots are there, out there. And then use the UV visible spectra for our samples were taken, which shows that the band gap for the pure ZNO, we know it is around 3.2 to 3.4 electron volt. However, for 2% copper dope, it becomes 3.09 electron volt. For 4%, it is 3.1 electron volt, and then it is 3.02 electron volt for 6% copper dope sample. Our positron lifetime data are tabulated out here. We are in the process of analyzing these data. Okay, so you can see there are two lifetimes, T1 and T2. This is order of 166 picoseconds. This is order of 292 picoseconds with their corresponding intensities, and they are for different samples that we have. And then I would like to say that we need to take some more positron measurement, especially the lifetime spectra and coincident Doppler measurement, and do the analysis before arriving at some conclusion. So we are sorry to state that we are unable to do further positron spectroscopic and magnetization studies due to the present situation arising out of COVID-19 pandemic. Once the situation gets normal, we hope to do the rest of the measurement, try to get it correlated to our Dept calculation and come up with a conclusion. So I would like to thank all of you for giving me the chance to present before you my paper. So thank you.
Thanks a lot, Dr. Haldar. Indeed, we also wish that this pandemic situation goes off and you can get back to, and we will get to know lots of interesting results which are coming up. Thanks a lot.
Okay.
With this, we have almost reached at the end part of today's session. Before we conclude, the vote of thanks is the only thing which is remaining. So for that, I would like to invite the coordinator of IQAC of our college, as well as the head of Department of Bengali, Dr. Nilanjana Bhattacharya, for our vote of thanks. Ma'am, please come and.
Thank you, Abru. Honorable Principal Sir, esteemed invited speakers, our most valued participating teachers, my colleagues, beloved students, it's my privilege to have been asked to propose a vote of thanks at the end of day one program of this two-day international webinar on recent trends in nanomaterials and nanobiomaterials organized by Department of Physics, Narajole Raj College. On behalf of Internal Quality Assurance Cell, Narajole Raj College, and entire webinar team, I am expressing my sincere regards to our Honorable Principal, Dr. Anupam Parua, for his valuable advice and continuous support. Thank you, sir, for your presence and inspiring words. I would like to convey my deep regards to Dr. Shubhadeep Ghosh, Associate Professor, School of Chemical Sciences, Nizar, Odisha, for his remarkable keynote address on Insight to the Photophysical Process in Semiconductor, Quantum Dots, and Carbon Dots. I am expressing my gratitude to Dr. Ravikiran Saripalli, Postdoctoral Fellow, Department of Quantum Information and Nonlinear Optics, Tulane University, United States of America, for his radiant presentation and explanation on manipulation of light through interaction with nanomaterials. I must mention our deep sense of appreciation to Dr. Udayanaran Maiti, Assistant Professor, Department of Physics, IIT Guwahati, for his presentation and discussion on the topic, two-dimensional atomic layers, graphene and beyond. I would like to acknowledge our gratitude to Dr. Kollul Roy, Postdoctoral Fellow, Center for Advanced 2D Materials, National University of Singapore, for his excellent speech and presentation on photons, plasmons, and nanomaterial size gaps. I would like to thank all three young teachers, Dr. Pijushkanti Shamantu from PK College, Kontai, Dr. M. Krishnaveni, MS University, Tamil Nadu, Dr. Bidyut Haldar from Damdam Motijil College, for their vibrant paper presentations. I want to express my heartfelt gratitude to all participating teachers and students of our college and from other institutions for their patient listening, with whom we are able to maintain the true academic spirit of the program. Thank you. I must say, I remain obligated to our technology committee, consisting of Professor Borun Raut, Dr. Sheikh Muhammad Aziz, Dr. Shreyushi Jana, Dr. Obrodip Pradhan, Dr. Poulami Odhikari Mukherjee, Professor Tanmay Goswami. Without your tireless efforts, this webinar would not have been possible. Thank you very much. And last but not least, my colleagues of Department of Physics, Dr. Taponindu Kamilla, convener of this seminar, Dr. Obrodip Pradhan, special thanks to him for his nice and flawless coordination of the program, Dr. Arif Iqbal Mollik, Professor Shurojit Dhara, Professor Shumam Tohait, and obviously Sri Shufal Kumar Barik. I am conveying my warm wishes to them for their very sincere and enthusiastic approach, which made this endeavor actually possible. Once again, thanks to all for making today's program a successful. Meet you tomorrow at the same time. So stay home, stay safe, have a nice day. I am signing off here.
Thank you, ma'am, for a vote of thanks. So with this, we have reached at the conclusion of today's part. So see you all tomorrow again at 9:15 to 9:30. Stay safe and stay well. And please come and make this webinar a grand success. Thank you all.
Hello, sir. Hello. Hello.
Yes, with this.
Sir, what is the feedback link? Where is the feedback link?
Feedback link. Papunendu sir,
Of today's session.
Can you say something about that? What she is asking?
Hello.
Yeah, feedback link will be sent. Feedback link will be sent in WhatsApp group. Okay.
Okay, sir. Thank you. Okay.
Okay. With this, I would like to conclude today's talk. Stay safe and stay well. We'll meet again tomorrow at 9:15 to 9:30. Thank you.
Close the session.
Yes, close করে দিন। আমি লগ আউট করছি।
Okay.